Hello there and welcome to Science for Sleep, where curiosity gets comfortable, science takes its time, and the universe becomes a little easier to explore at the end of a long day. Tonight, we're turning our attention towards some of the most powerful events ever detected in the cosmos. Not black holes, not supernovae, not even entire galaxies. Instead, we're going to spend some time with brief flashes of energy so intense that for a few moments, they can outshine nearly everything else in the observable universe. They're called gamma-ray bursts. Now, that name might sound a bit technical, perhaps even slightly intimidating, but don't worry. By the time we're finished, you'll know exactly why astronomers became so fascinated by them, how they were discovered completely by accident, and why these extraordinary explosions continue to puzzle scientists even today. Before we begin though, I'd love to know something. Where in the world are you listening from tonight? Are you tucked into bed while rain taps gently against a window, sitting quietly in a chair after a busy day? Maybe you're listening during a late-night drive beneath a sky full of stars. And what time is it where you are right now? It's a fitting question for tonight's journey, because the events we're about to discuss happened across vast stretches of time. Some of the gamma-ray bursts we'll encounter began their journeys toward Earth billions of years ago, long before humans existed, long before our planet looked anything like it does today. The light from those distant explosions travelled through expanding space for unimaginable lengths of time before finally reaching our instruments. And somehow, after crossing billions of light years, it arrived precisely when we were ready to notice it. If you find this voyage relaxing, interesting, or simply a pleasant way to unwind before sleep, I'd be very grateful if you gave the video a like and perhaps subscribed as well. It helps this little corner of calm science find other curious people who enjoy ending their day with questions about the universe. Now settle in. Allow your shoulders to relax. Let the concerns of the day drift a little farther into the background. Tonight we're going to talk about explosions. Not the loud kind, fortunately. Not the sort that rattle windows or wake neighbours. The explosions we'll be discussing occur so far away that they arrive as faint signals detected by spacecraft orbiting Earth. Yet despite their distance, they are among the most energetic events ever observed. To appreciate how remarkable that is, let's begin with something familiar. Imagine someone switches on a flashlight. Simple enough. A small amount of energy leaves the bulb and travels outward as light. Now imagine a lighthouse. Far brighter, far more powerful. The beam can be seen for many kilometers. Next, imagine the sun. Every second, our star releases more energy than humanity could use in millions of years. The amount of power involved is almost impossible to picture. Yet compared with a gamma-ray burst, even the sun begins to look surprisingly modest. That sounds exaggerated. Whenever people hear statements like that, a natural reaction is skepticism. Surely nothing can be that powerful. Surely astronomers are using dramatic language. As it turns out, if anything, astronomers often struggle to explain just how extreme these events really are. The difficulty isn't that the science is unclear. The difficulty is that our brains evolved to think about everyday objects, trees, houses, roads, weather. A gamma-ray burst belongs to an entirely different category of experience. There is no direct comparison available in ordinary life. You can't visit one. You can't safely observe one nearby. You can't recreate one in a laboratory. You certainly wouldn't want one occurring close to Earth. So scientists have spent decades trying to build intuitive ways of understanding them. One comparison often used involves the lifetime energy output of the sun. Our star shines continuously, day after day, year after year, century after century, million year after million year. The sun has been producing energy for approximately 4.6 billion years. That is an extraordinarily long time. And yet some gamma-ray bursts release comparable amounts of energy in mere seconds. Just pause for a moment and let that idea settle. Billions of years of stellar energy output, compressed into a time span shorter than a television commercial. Naturally, when astronomers first encountered evidence for these objects, many were stunned. Some wondered whether their instruments were malfunctioning. Others suspected entirely different explanations. After all, if a detector suddenly reports an event that appears impossibly bright, the first assumption is often that something has gone wrong. Usually, extraordinary measurements turn out to have ordinary causes. A sensor fails, a calibration error appears, a software issue slips through unnoticed. Science advances by being cautious. Scientists are generally reluctant to announce revolutionary discoveries without overwhelming evidence. Yet gamma-ray bursts refused to go away. Again and again, detectors observed brief flashes of intense gamma radiation arriving from deep space. Not from Earth, not from the Sun, not from any familiar source. Something out there was producing these astonishing signals, and nobody knew what. In some ways, that's one of the most enjoyable parts of scientific history. We often learn about discoveries after the mystery has already been solved. A textbook tells us what a thing is. A documentary explains how it works. Everything seems neat and organized. Reality is usually messier. When gamma-ray bursts first appeared, scientists didn't receive a helpful note from the universe explaining the answer. There was no cosmic instruction manual. There was only a puzzle, a very strange puzzle. Imagine receiving a series of postcards from an unknown sender. The postcards arrive unpredictably. They're brief, they contain very little information, and each one hints at something enormous happening somewhere beyond your sight. That was essentially the situation astronomers faced. Signals appeared, then vanished. A few seconds later they were gone. No obvious source, no clear explanation, just fleeting flashes from the darkness. Oddly enough, one reason gamma-ray bursts remained mysterious for so long was their brevity. You might assume longer events would be harder to study. In many cases, the opposite is true. If an object remains visible for days, weeks, or months, astronomers can point telescopes toward it and gather information. Gamma-ray bursts often appear and disappear almost immediately. Imagine trying to investigate a lightning strike that occurs on another continent and lasts only an instant. By the time you react, it's already over. For decades, this made gamma-ray bursts incredibly frustrating research targets. Astronomers knew something extraordinary was happening. They just couldn't catch enough details. And there's another interesting aspect to these events. Despite their incredible violence, most people have never heard of them. Black holes enjoy widespread fame. Supernovae appear regularly in documentaries. Planets attract endless attention. Gamma-ray bursts, meanwhile, remain relatively unknown outside astronomy circles. That's somewhat surprising because if we ranked cosmic phenomena by raw power, gamma-ray burst would sit near the very top of the list. Perhaps part of the reason is their fleeting nature. Human beings tend to form attachments to things that linger. Planets remain visible. Stars shine every night. Galaxies can be photographed and admired. Gamma-ray bursts arrive suddenly, announce themselves with astonishing intensity, and then fade away. They're more like cosmic fireworks than permanent landmarks. Except these fireworks would make any earthly display seem laughably tiny. The universe has a habit of operating on scales that challenge intuition. A mountain seems large until you compare it with a planet. A planet seems large until you compare it with a star. A star seems large until you compare it with a galaxy. And even galaxies begin to look small when viewed against the vast structure of the cosmos. Gamma-ray bursts belong to that tradition of scale expansion. Every time scientists thought they understood how energetic an explosion could become, nature appeared to respond with something even more extreme. There's something almost humorous about it. Humanity spends centuries building larger telescopes and more sophisticated instruments. We finally managed to glimpse distant corners of the universe. And what do we find? Events so powerful they force us to rethink our assumptions. It's as though the cosmos enjoys reminding us not to become too confident. Still, the story becomes even more fascinating when we consider where these bursts originate. They aren't random, they aren't supernatural, they aren't violations of physics. In fact, they emerge from processes that scientists increasingly understand. Massive stars, collapsing cores, colliding neutron stars, extreme environments where gravity, energy, and matter interact under conditions difficult to imagine. The challenge isn't that gamma-ray bursts are magical. The challenge is that they are real. Real events occurring in a real universe according to real physical laws. Sometimes reality is more astonishing than fiction. A science fiction writer inventing an explosion capable of briefly outshining entire galaxies might be accused of exaggeration. Then astronomers point their instruments toward the sky and discover nature already thought of it first. Of course, whenever people hear about immensely powerful cosmic events, another question quickly follows. Should we be worried? It's a reasonable concern. After all, an explosion capable of releasing such tremendous energy doesn't sound particularly friendly. The reassuring news is that space is extraordinarily large, really truly enormous. The distances separating stars are difficult to comprehend. The distances separating galaxies are even harder. Most gamma-ray bursts occur so far away that they pose no danger whatsoever. Their signals reach us as faint whispers after crossing billions of light years. Even then, those whispers are enough to reveal remarkable information. In many ways, astronomers act like detectives. They rarely visit the scenes they investigate. Instead, they study clues carried by light. A burst appears. Instruments record its properties. Researchers analyze the data. Gradually, a picture emerges. Piece by piece, the universe tells its story. And gamma-ray bursts have become some of the most valuable storytellers of all. They reveal how massive stars die. They reveal how exotic objects collide. They reveal conditions that existed billions of years ago. Some even provide glimpses into the early history of the cosmos itself. Not bad for something that might last only a few seconds. As remarkable as these explosions are, however, one detail makes their discovery story even better. Humanity wasn't actually looking for gamma-ray bursts when we found them. Their existence came to our attention through circumstances nobody expected. Several decades before, astronomers understood what gamma-ray bursts were. Before scientific conferences filled with debates about collapsing stars and neutron star collisions, before sophisticated space telescopes began tracking these extraordinary events across the cosmos, something very unexpected happened. The first people to discover gamma-ray bursts were not searching for distant exploding stars. They were not studying galaxies. They were not even conducting astronomy. Instead, they were helping monitor one of the most tense periods in modern history. To understand how gamma-ray bursts entered science, we need to travel back to the 1960s. The world looked very different then. The Cold War was underway. The United States and the Soviet Union were locked in a prolonged geopolitical rivalry. Both nations possessed nuclear weapons powerful enough to devastate entire cities, and both were deeply concerned about whether the other side might secretly test new devices. This concern eventually led to an important agreement. In 1963, several nations signed the Partial Nuclear Test Ban Treaty. The treaty prohibited nuclear weapon tests in the atmosphere, underwater, and in outer space. Only underground testing remained permitted. Signing a treaty, however, is one thing. Verifying compliance is another. Governments wanted a reliable way to ensure nobody was secretly conducting forbidden nuclear explosions beyond Earth's atmosphere. As a result, the United States developed a series of spacecraft known as the Vela satellites. The name Vela comes from a constellation in the southern sky, but the satellites themselves had a very practical mission. They were essentially watchdogs. Their job was to detect evidence of nuclear detonations occurring in space. The concept was straightforward. Nuclear explosions release distinctive bursts of high-energy radiation, including gamma rays. If a country attempted to conduct a secret test in orbit, or elsewhere beyond Earth, the Vela satellites would notice. The spacecraft carried sensitive instruments specifically designed to detect these energetic signals. Everything seemed logical. The satellites would monitor space. If they observed gamma rays characteristic of a nuclear explosion, investigators could determine what happened. Problem solved. Except reality had other plans. In July of 1967, one of the Vela satellites recorded something unusual. Actually, several satellites recorded it. The instruments detected a brief burst of gamma radiation. At first glance, this might have sounded like exactly what they were built to find. Yet something was wrong. The signal didn't behave the way a nuclear explosion should. Scientists began examining the data. They checked the instruments. They reviewed the measurements. They looked for possible errors. Then they discovered something even stranger. The burst had arrived from a direction that didn't make sense. It wasn't coming from Earth. It wasn't originating near Earth. And it didn't appear to be coming from the Sun either. This was unexpected. The Vela satellites had been designed to monitor human activity. Nobody had seriously anticipated that they might uncover an entirely new cosmic phenomenon. Initially, researchers remained cautious. Scientific caution is usually a good idea when dealing with surprising observations. One strange signal could result from instrument malfunction. Spacecraft operate in a challenging environment. Sensors occasionally misbehave. Electronic systems experience glitches. False alarms happen. The team needed more evidence. Fortunately, the universe was willing to provide it. Over time, additional bursts appeared. Then more and more. Each one looked similar. Brief flashes of intense gamma radiation. Appearing unexpectedly. Arriving from different regions of the sky. Not matching known astronomical sources. Not matching nuclear weapons. Not matching anything scientists understood. Imagine being part of that research team. Your assignment involves monitoring compliance with an international treaty. You expect routine technical work. Instead, your instruments begin detecting mysterious explosions somewhere beyond the solar system. That's not a normal day at the office. Normal. The situation became increasingly puzzling. Researchers attempted to identify possible explanations. Perhaps the burst came from the sun. After all, the sun can produce energetic flares, but the data didn't fit. The burst appeared in locations inconsistent with solar activity. Maybe they originated from planets. Again, the evidence disagreed. Could they be coming from nearby stars? Possibly. Yet there was no convincing proof. At this stage, scientists faced a genuine mystery. They knew the signals existed. They knew the signals were real. They simply didn't know what was producing them. One detail made the problem especially difficult. Gamma rays are challenging to study. Visible light can be focused using mirrors and lenses. Radio waves can be collected with large antennas. Gamma rays behave differently. They carry enormous amounts of energy and pass through many materials that would stop ordinary light. Detecting them requires specialized instruments. Determining their exact origin is even harder. As a result, the Vela satellites could confirm the burst existed, but pinpointing their locations with great precision remained difficult. It's a bit like hearing a distant firework while standing in a dense fog. You know something happened. You know it was loud. You have a rough idea of the direction, but finding the exact source remains challenging. Scientists spent years wrestling with this problem. More bursts arrived. The mystery deepened. Nobody could decide whether these events originated nearby or incredibly far away. That distinction mattered enormously. If the burst came from within our own galaxy, they would be impressive but manageable. If they came from distant galaxies, the energy involved would be almost unimaginable. Without accurate distances, researchers couldn't calculate how powerful the explosions really were. And so, throughout the late 1960s and early 1970s, gamma-ray bursts occupied a strange scientific position. They were undeniably real, yet almost everything important about them remained unknown. Where did they come from? How often did they occur? What objects produced them? How energetic were they? No one had satisfactory answers. Interestingly, the government classified much of the Vela program because of its military purpose. The satellites were part of national security operations. Consequently, the discovery of gamma-ray bursts didn't immediately become public knowledge. For several years, the scientific community at large remained unaware of what the Vela instruments had found. The data existed, the mystery existed, but the broader astronomical world had not yet joined the investigation. Eventually, that changed. In 1973, researchers published the first scientific paper describing the phenomenon. Astronomers around the world suddenly learned that mysterious gamma-ray flashes were appearing in space. The response was immediate, questions multiplied rapidly. Ideas emerged from every direction. Some scientists suggested neutron stars, others proposed black holes, some suspected entirely new categories of objects. A few ideas turned out to be wildly incorrect. That happens whenever researchers encounter something unfamiliar. Science progresses through possibilities. Many possibilities fail, a few survive. At the time, nobody knew which explanations would endure. What followed became one of the longest-running mysteries in modern astronomy. For decades, gamma-ray bursts resisted easy interpretation. New observations arrived, new theories appeared, arguments filled conference halls. Researchers examined every clue they could find, yet the central mystery remained stubbornly intact. One reason the debate lasted so long was the extraordinary diversity of proposed explanations. When scientists lack crucial information, imagination tends to expand. Some theories suggested gamma-ray bursts originated from neutron stars within the Milky Way. Others placed them much farther away. A few proposals involved exotic physics. Some invoked entirely new astrophysical processes. Looking back today, it's easy to forget how little information researchers possessed. Modern astronomy often presents discoveries as neat stories with clear answers. The reality is usually much messier. For years, gamma-ray bursts resembled pieces of a puzzle, scattered across a table without the picture on the box. Researchers knew the pieces connected somehow. They simply couldn't see the complete image. Another complication involved timing. Gamma-ray bursts were frustratingly brief. Some lasted only fractions of a second. Others persisted for several seconds or minutes. Then they disappeared. Unlike stars, they didn't remain available for extended observation. Astronomers couldn't simply point telescopes at them whenever convenient. They had to react quickly, extremely quickly. And in the early decades of gamma-ray burst research, that was difficult. Communication systems were slower. Space-based detection networks were less sophisticated. By the time scientists learned a burst had occurred, the event was often long gone. Imagine trying to study lightning using a camera that develops film several days later. You'd know lightning exists, you'd know it happened. But capturing detailed information would be challenging. Gamma-ray burst researchers faced similar frustrations. Even so, progress continued. Each new detection added another clue. Patterns gradually emerged. Scientists noticed that some bursts lasted longer than others. Some appeared brighter. Some displayed different energy characteristics. The data hinted that multiple processes might be involved. The universe rarely provides simple mysteries. It prefers complicated ones. Meanwhile, technology improved. New satellites joined the search. Detection capabilities expanded. Computers became more powerful. Researchers developed increasingly sophisticated methods for analysing observations. Step by step, the fog began to lift. Yet one major question remained unresolved. Where exactly were these bursts occurring? The answer carried enormous consequences. Suppose gamma-ray bursts originated within our galaxy. That would imply one level of energy. Suppose they originated billions of light years away. That would imply something dramatically different. The farther away an object is, the more powerful it must be to appear bright from Earth. Distance transforms interpretation. A flashlight visible from across a room is ordinary. A flashlight visible from another continent would be impossible. Gamma-ray bursts seem to occupy a similar dilemma. Scientists couldn't determine whether they were observing relatively nearby events, or some of the most energetic explosions in existence. Then additional observations provided an important clue. When researchers mapped burst locations across the sky, they noticed something intriguing. The events appeared distributed almost uniformly, not concentrated along the plane of the Milky Way, not clustered around nearby regions. Instead, they seemed to come from everywhere, every direction, every corner of the sky. This observation created fresh excitement. If the bursts originated throughout the universe, rather than within our local neighbourhood, then their true power might be extraordinary. The implications were staggering. Still, evidence remained incomplete. Researchers needed better measurements, better localization, better instruments. Science often advances this way, not through sudden revelation, but through gradual accumulation. One clue becomes 2. 2 become 10. 10 become 1,000. Eventually, uncertainty narrows enough for a clearer picture to emerge. Yet throughout all those years, one fact remained delightfully ironic. Humanity discovered gamma-ray bursts entirely by accident. No astronomer submitted a proposal specifically requesting military satellites search for unknown cosmic explosions. No committee designed the Vela program with gamma-ray burst astronomy in mind. The discovery emerged as an unintended consequence of a completely different mission. History contains many examples of accidental discoveries: penicillin, microwave ovens, cosmic microwave background radiation. Gamma-ray bursts belong comfortably on that list. Researchers searching for evidence of nuclear testing stumbled across one of the greatest astronomical mysteries of the 20th century. There's something wonderfully human about that. We set out looking for one thing. The universe hands us another. Sometimes the most important discoveries arrive uninvited. In fact, if the Cold War had unfolded differently, gamma-ray bursts might have remained unknown for much longer, without the treaty, without the satellites. Without those sensitive detectors scanning the sky, the first clues could easily have gone unnoticed. Instead, a geopolitical rivalry inadvertently opened a new window onto the cosmos. And what appeared through that window turned out to be far more extraordinary than anyone expected. The mystery was now public. Astronomers around the world were paying attention. More sophisticated instruments would soon join the search. Fresh evidence would arrive. Theories would rise and fall. And gradually scientists would begin uncovering the true nature of these astonishing flashes. Not every explosion in the universe is created equal. A firecracker and a volcano are both explosions, but nobody would confuse one with the other. A lightning strike and a nuclear detonation both release energy, yet they belong to completely different categories of power. The same principle applies in astronomy. The universe is full of explosive events. Stars erupt, black holes consume matter. Supernovae tear apart entire suns. Galaxies collide over hundreds of millions of years. Violent processes occur throughout space every single day. Yet among all these dramatic phenomena, gamma-ray bursts occupy a special place. When astronomers talk about the most powerful explosions ever detected, they're usually talking about gamma-ray bursts. That raises an obvious question. What exactly is a gamma-ray burst? The name itself offers a few clues. Let's begin with the first part. Gamma rays. Most people are familiar with visible light because it's the portion of the electromagnetic spectrum our eyes can detect. The colours of a sunset, the glow of a lamp, the screen you're looking at right now, all of these involve visible light. What many people don't realise is that visible light represents only a tiny fraction of a much larger family. The universe produces many different forms of electromagnetic radiation: radio waves, microwaves, infrared radiation, visible light. Ultraviolet light. X-rays, and finally, gamma rays. All of these are fundamentally the same thing. They're all electromagnetic waves travelling through space at the speed of light. The difference lies in their energy. Radio waves carry relatively little energy. Gamma rays carry enormous amounts. If the electromagnetic spectrum were arranged like a piano keyboard, radio waves would occupy the deep, low notes at one end, while gamma rays would sit at the highest and most energetic end imaginable. Another way to think about it is frequency. Gamma rays vibrate extraordinarily rapidly. Each wave carries tremendous energy compared with ordinary visible light. A single gamma ray photon can possess hundreds of thousands or even millions of times more energy than a photon of visible light. This makes gamma rays extremely powerful. It also makes them dangerous. Fortunately for us, Earth's atmosphere does a remarkable job protecting life from most incoming gamma radiation. Without that protection, life on our planet would face a much harsher environment. The atmosphere acts like a giant shield, absorbing many forms of high-energy radiation before they reach the ground. Ironically, that protective shield creates a challenge for astronomers. Because gamma rays don't easily reach Earth's surface, scientists cannot simply place a telescope on a mountain and observe them directly. Instead, they must send instruments into space. This is one reason gamma ray astronomy developed relatively late compared with optical astronomy. People have been studying visible stars for thousands of years. Gamma rays remained largely invisible until the space age. Once scientists finally placed detectors above the atmosphere, an entirely new universe emerged. Suddenly, astronomers could see energetic phenomena that had been hidden from human observation throughout history. Among the most surprising discoveries were the mysterious flashes detected by the Vela satellites. Those flashes would eventually become known as gamma ray bursts. The second part of the name is equally important. Burst, not steady emission, not continuous radiation. A burst, something appears, something releases an enormous amount of energy, then it fades. The event is brief, in some cases, astonishingly brief. One of the most fascinating aspects of gamma ray bursts is their duration. Many people imagine cosmic events lasting centuries or millennia. Stars live for billions of years. Galaxies evolve over immense stretches of time. Even supernova remnants can remain visible for thousands of years. Gamma ray bursts often operate on entirely different timescales. Some last only a fraction of a second. Others persist for several seconds. A few continue for minutes. Then they're gone. The most powerful explosions in the universe frequently announce themselves in less time than it takes to pour a cup of tea. That's one of the reasons they remained mysterious for so long. Astronomers simply didn't have much time to observe them. Imagine trying to understand lightning if each bolt occurred on the far side of the planet and lasted only an instant. You'd know something happened. You might detect its presence, but gathering detailed information would be difficult. Gamma ray burst researchers faced exactly that problem for decades. The bursts appeared unexpectedly. They delivered tremendous energy. Then they vanished. Yet despite their brief duration, they leave behind clues. In astronomy, light is information. Every photon carries a message. The color of the light matters. The intensity matters. The timing matters. The way brightness changes matters. Scientists learned to extract remarkable amounts of information from these fleeting signals. Gradually, a picture began to emerge. Gamma ray bursts weren't all identical. In fact, researchers noticed something interesting. Some bursts tended to be very short. Others lasted much longer. At first, this seemed like a minor detail. Eventually, it became one of the most important clues in the entire mystery. Today, astronomers generally divide gamma ray bursts into two major categories: short gamma ray bursts and long gamma ray bursts. The dividing line is roughly 2 seconds. If a burst lasts less than about 2 seconds, it usually belongs to the short category. If it lasts longer, it typically falls into the long category. That distinction might sound simple, In reality, it revealed that nature was producing gamma-ray bursts through at least 2 different mechanisms. It's a little like discovering that earthquakes and volcanic eruptions can both shake the ground, yet arise from different causes. The outward effect may appear similar. The underlying process is not. We'll explore those origins in detail later. For now, it's enough to understand that gamma-ray bursts are not one single phenomenon. They're a family of related phenomena connected by their production of intense gamma radiation. The story becomes even more impressive when we consider brightness. Astronomers often use the word luminosity when discussing how much energy an object emits. The sun is luminous. A supernova is highly luminous. A gamma-ray burst can reach levels of luminosity that seem almost absurd. For a brief period, a single gamma-ray burst can outshine an entire galaxy. Think about that carefully. Not a single star, not a cluster of stars, an entire galaxy. Hundreds of billions of stars shining together. And yet, for a short time, a gamma-ray burst may produce more energy than all of them combined. This statement sounds impossible at first. Many people assume there must be some catch, and there is. A very important one. Gamma-ray bursts do not radiate equally in every direction. They produce highly focused beams. To understand why this matters, imagine 2 flashlights. The first spreads light in all directions. The second concentrates nearly all its light into a narrow beam. The second flashlight appears much brighter when viewed directly from the front. Gamma-ray bursts behave similarly. Much of their energy becomes concentrated into powerful jets. These jets travel outward at speeds extremely close to the speed of light. Astronomers refer to such motion as relativistic. Relativistic speeds produce some very unusual effects. Energy becomes concentrated. Brightness increases dramatically. Observations become highly dependent on viewing angle. If one of those jets happens to point toward Earth, astronomers detect an extraordinarily bright burst. If the jet points elsewhere, we may never notice the event at all. This realization solved another major puzzle. For years, scientists wondered why gamma-ray bursts seemed so rare. The answer was that many were simply invisible to us. The universe might produce far more gamma-ray bursts than we actually observe. We're only seeing the ones whose beams happen to intersect our location. It's a bit like standing on a coastline at night while distant lighthouses rotate. You only notice each lighthouse when its beam sweeps across your position. The lighthouse shines continuously. Your visibility of it depends on geometry. Gamma-ray bursts operate according to a similar principle, although on vastly larger scales. Another important feature involves afterglows. When people first hear the term gamma-ray burst, they often imagine a single flash and nothing more. The reality is slightly more complicated. After the initial burst, many events continue producing radiation at other wavelengths. Astronomers call this emission an afterglow. The afterglow can appear in X-rays, visible light, infrared radiation, radio waves. Sometimes these afterglows remain detectable for days, weeks, or even longer. This was an enormous breakthrough for researchers. Remember the original problem. Gamma-ray bursts disappeared almost immediately. Studying them was extremely difficult. Afterglows changed everything. Now astronomers could identify the location of a burst and continue observing the aftermath long after the gamma rays had faded. Imagine hearing a sudden crash in another room. The sound itself lasts only an instant. But if you enter the room afterward, you can examine the evidence, the broken objects, the scattered debris, the signs of what happened. Afterglows provide a similar opportunity. The burst itself may be brief. The aftermath remains available for investigation. Through afterglow observations, scientists finally began identifying host galaxies. Distances could be measured. Energy estimates became more reliable. The mystery started yielding answers. One of the most surprising discoveries involved just how far away many gamma-ray bursts actually are. Some originate billions of light-years from Earth. That means the light reaching our detectors began its journey billions of years ago. In many cases, the explosion occurred long before complex life existed on Earth. The photons travelled across expanding space for unimaginable spans of time before finally arriving at a spacecraft orbiting our planet. There's something remarkable about that. A star dies in a distant galaxy. A beam of gamma rays begins racing across the cosmos. Entire civilizations could rise and fall during its journey. Species evolve, continents shift, mountains erode. Then, billions of years later, a detector registers a brief signal. A tiny spike appears on a computer screen. And scientists suddenly know that something extraordinary happened in a galaxy unimaginably far away. Gamma-ray bursts are therefore more than explosions. They are messages. Not intentional messages, of course. The universe isn't sending letters. Yet every burst carries information from another place and another time. Each one tells us something about the conditions that existed when the event occurred. Because many bursts originate at extreme distances, they also allow astronomers to study the early universe. In effect, gamma-ray bursts function as cosmic flashlights. Their light passes through gas and matter on its way toward Earth. By analysing that light, scientists learn about environments that would otherwise remain difficult to observe. This makes gamma-ray bursts useful even beyond their own intrinsic interest. They help reveal the history of the cosmos. Another misconception deserves attention. People sometimes imagine gamma-ray bursts as giant fireballs expanding outward in all directions. The reality is more complex. The central engines driving these events are among the most extreme objects known: collapsing stellar cores, neutron stars, black holes, intense magnetic fields. Matter accelerated to nearly light speed. The explosions involve physics operating under extraordinary conditions. These are not merely larger versions of ordinary explosions. They belong to a category all their own. Perhaps the easiest way to appreciate this is through comparison. Consider a campfire, then compare it with a lightning bolt. Both involve energy release, yet they function differently. Now compare lightning with a nuclear detonation. Again, vastly different scales and mechanisms. Gamma-ray bursts represent another leap altogether. They arise from environments so extreme that everyday intuition becomes unreliable, and yet, despite their incredible power, they remain governed by the laws of physics. That's one of the most satisfying aspects of astronomy. The universe often appears strange, sometimes even frighteningly strange. But beneath the strangeness lies consistency. Gravity behaves according to physical laws, radiation behaves according to physical laws. Matter behaves according to physical laws. Gamma-ray bursts may seem exotic, but they are ultimately products of those same universal principles. Scientists didn't solve their mystery by invoking magic. They solved it through observation, mathematics, engineering, and patience. Lots of patience. Today, astronomers understand far more about gamma-ray bursts than researchers did during the Vela era. Yet important questions remain. Why do some bursts become extraordinarily powerful? How exactly do relativistic jets form? What determines their structure? Are there categories we still haven't discovered? The universe continues to keep a few secrets. Still, we've now arrived at a basic definition. A gamma-ray burst is a brief but extraordinarily intense flash of gamma radiation produced during some of the most extreme events in the universe. It can release astonishing amounts of energy. It often creates powerful relativistic jets. It may be visible across billions of light years. And for a short period, it can become one of the brightest phenomena in existence. Naturally, once scientists realized what they were dealing with, another question immediately followed. If gamma-ray bursts are truly that powerful, just how powerful are we talking about? A strange thing happens whenever astronomers try to explain gamma-ray bursts to the public. The conversation usually begins quite calmly. Scientists mention a powerful explosion. People nod politely. Then they hear a comparison. Perhaps the burst released more energy in a few seconds than the sun will produce over its entire lifetime. At that point, eyebrows tend to rise. Then comes another comparison. A single gamma-ray burst can briefly outshine an entire galaxy. Now people start wondering whether astronomers have accidentally misplaced a decimal point somewhere. The truth is that gamma-ray bursts occupy a category of power so extreme that ordinary language struggles to keep up. Human beings evolved to understand everyday scales. We understand the size of a room, the distance to a nearby town, the speed of a moving car. Even very intelligent people encounter difficulties when numbers become truly enormous. Astronomy forces us into that territory constantly. Gamma-ray bursts might be one of the best examples. To appreciate their power, let's start somewhere familiar: our Sun. The Sun is not a small object. It contains approximately 99.8% of all the mass in the solar system. Every second, deep within its core, nuclear fusion converts millions of tons of matter into energy. That energy radiates outward in every direction. The sunlight warming your skin, growing plants, illuminating clouds and making life possible ultimately originates from those fusion reactions. The amount of power involved is staggering. Each second, the Sun releases roughly 380 septillion watts of energy. That's a number so large that most people immediately stop visualizing it. And honestly, that's understandable. The human brain didn't evolve to picture septillions of anything. What's important is this: the Sun is unimaginably powerful. Yet compared with a gamma-ray burst, it can look surprisingly modest. Imagine taking all the energy the Sun will generate during its entire lifetime. Not a day, not a year, not a century. Its entire existence. From the moment fusion first ignited in its core until the distant future when it eventually exhausts its fuel. Now imagine releasing a substantial fraction of that energy in mere seconds. That begins to approach the territory occupied by gamma-ray bursts. Even among professional astronomers, this comparison remains astonishing. After all, stars are already among the most powerful objects in the universe. If something makes a star look ordinary, that something deserves attention. Yet gamma-ray bursts don't merely compete with stars, they compete with galaxies. Let's think about a galaxy for a moment. The Milky Way contains somewhere between 100 and 400 billion stars. Nobody knows the exact number. Astronomers continue refining their estimates. Regardless of the precise figure, we're talking about hundreds of billions of suns. Every one of those stars produces energy. Some are larger than our Sun, some are smaller. Collectively, they generate an extraordinary amount of light. When you look up at the night sky and see the faint band of the Milky Way stretching overhead, you're seeing the combined glow of countless stars. Now consider another galaxy, perhaps one located billions of light years away. It might contain hundreds of billions of stars as well. Entire populations of suns, nebulae, star clusters, black holes, all shining together. And yet, for a brief period, a gamma-ray burst can produce more observable energy than all of it. Not permanently, not for years, but for a short time, yes. One explosion, one event, one dying star or catastrophic collision, outshining a galaxy. That's an extraordinary statement. What's even more remarkable is that astronomers aren't speaking metaphorically. They mean it literally. Measurements support it. Detectors record it. Physics explains it. Nature simply happens to be capable of producing explosions that are powerful. One reason this seems difficult to grasp is that we're accustomed to associating size with power. Large things produce large effects. Small things produce small effects. Gamma-ray bursts challenge that intuition. The central engine responsible for a burst may occupy a region smaller than a city. Yet the energy involved can exceed that produced by entire galaxies. It's not about physical size, it's about efficiency. Specifically, how efficiently matter can be converted into energy. Einstein gave us the famous equation E=mc². Most people recognize the equation even if they don't use it regularly. The equation tells us that matter and energy are deeply connected. a surprisingly small amount of mass can produce an enormous amount of energy. The speed of light squared is a very large number. Multiply even a modest amount of mass by that value, and the resulting energy becomes immense. Most everyday processes are not particularly efficient at converting mass into energy. Burning wood releases energy, but only a tiny fraction of the wood's mass becomes energy. Nuclear reactions are far more efficient. That's why nuclear power plants and nuclear weapons can produce such dramatic effects. Gamma-ray bursts operate in environments where nature pushes efficiency toward extraordinary levels. The result is an energy release unlike almost anything else we observe. Still, discussing energy alone can feel abstract. Let's try another perspective. Imagine the most powerful earthquake ever recorded. Now imagine the most powerful volcanic eruption in history. Add the largest hurricanes. Add every thunderstorm occurring across Earth. Add every human-made explosion ever produced. The total still falls absurdly short of a typical gamma-ray burst. In fact, the comparison isn't even close. Earthly disasters feel enormous because we live on Earth. From a cosmic perspective, they barely register. A gamma-ray burst belongs to a completely different league. This is one reason astronomers often describe them as cosmic catastrophes. The word catastrophe may sound dramatic. In this context, it is entirely justified. Something truly catastrophic has occurred when a gamma-ray burst appears. A massive star has died, or two neutron stars have collided, or some other extreme astrophysical process has unfolded. Whatever the cause, nature has unleashed one of its most violent events. Interestingly, the bursts themselves are usually invisible to human eyes. That surprises many people. After hearing about such incredible power, people naturally imagine spectacular visual displays dominating the sky. The problem is that most of the energy emerges as gamma radiation. Human vision cannot detect gamma rays. Our eyes evolved to perceive visible light. Gamma rays occupy a completely different portion of the electromagnetic spectrum. As a result, many of the most energetic events in the universe occur entirely beyond direct human perception. Without specialized instruments, we wouldn't know they happened. There's something slightly humbling about that. The universe contains phenomena so powerful they can outshine galaxies. Yet we remain completely unaware of them until technology extends our senses. Gamma-ray astronomy essentially provides humanity with a new set of eyes capable of seeing some of the most energetic processes in existence. Another important factor complicates power estimates. Earlier, we discussed relativistic jets. These jets are crucial. Without them, gamma-ray bursts would appear very different. Imagine a light bulb. It radiates in all directions. Energy spreads outward uniformly. Now imagine a flashlight. The same amount of energy becomes concentrated into a narrow beam. The flashlight appears brighter when viewed directly from the front because the energy isn't wasted illuminating unnecessary directions. Gamma-ray bursts take this principle to extraordinary extremes. Much of their energy becomes focused into narrow jets moving at nearly the speed of light. When one of those jets points toward Earth, astronomers observe an exceptionally bright event. The concentration amplifies the apparent intensity. This means that part of a gamma-ray burst's astonishing brightness results from geometry. The energy isn't distributed equally throughout space. It's focused, directed, concentrated. Even after accounting for this effect, however, the bursts remain among the most energetic phenomena known. The correction helps. It doesn't eliminate the awe. Consider a typical long-duration gamma-ray burst. During its brief active period, the event may release as much energy as the Sun produces over billions of years, and it does so while creating jets travelling at speeds incredibly close to the universal speed limit. Nothing about that sentence sounds ordinary. Everything about it sounds extreme, because it is. Scientists occasionally encounter events so unusual that existing terminology struggles to describe them. Gamma-ray bursts belong in that category. This became particularly obvious as detection technology improved. During the early years of gamma-ray astronomy, researchers already suspected the bursts were powerful. Then more data arrived. Distances became clearer, energy calculations improved, and the situation became even more surprising. Some bursts appeared far more energetic than initial estimates suggested. The universe once again refused to be modest. A useful comparison involves supernovae. Supernovae are among the most famous explosions in astronomy. When a massive star dies, the resulting explosion can briefly outshine an entire galaxy. That's already impressive. For decades, supernovae represented the benchmark for stellar violence. Then astronomers realized that some gamma-ray bursts surpassed even those events, not merely matching them, exceeding them. In fact, certain gamma-ray bursts appear associated with particularly energetic supernovae called hypernovae. The name itself tells the story. When scientists start adding prefixes like hyper to existing categories of explosion, you know something unusual is happening. A hypernova is not simply a larger supernova. It represents a more extreme process involving exceptionally massive stars and extraordinary energy release. Many long-duration gamma-ray bursts appear connected to such events. The star doesn't merely explode, its core collapses, a black hole or neutron star forms, powerful jets erupt outward, and a gamma-ray burst is born. The result is one of the briefest yet most violent catastrophes nature can produce. The brevity is particularly fascinating. Human intuition often associates duration with significance. Long events feel important. Short events feel minor. Gamma-ray bursts invert that expectation. Some of the most powerful events in existence occur in seconds. A cosmic drama unfolds. An immense amount of energy is released. The event reshapes its surroundings, and then it's over. At least from the perspective of the initial burst. The aftermath continues. Afterglows persist. Shock waves expand. Matter interacts with surrounding material, but the main event happens astonishingly quickly. There's an interesting lesson hidden in that fact. Nature doesn't always need time to accomplish dramatic things. Sometimes extraordinary changes occur almost instantly. A star may spend millions of years evolving toward a particular fate. Then, within seconds, everything changes. One moment the star exists. The next, it has become something entirely different. The gamma-ray burst marks that transition. Astronomers occasionally describe these events as cosmic lighthouses, not because they guide navigation, but because they can be seen across extraordinary distances. A sufficiently powerful burst may remain detectable even after travelling billions of light years. Think about what that means. The signal begins its journey in a distant galaxy. It crosses intergalactic space. It survives encounters with gas clouds and cosmic structures. It continues travelling for billions of years. Eventually, a detector orbiting Earth notices it. The burst is so energetic that even after losing intensity across unimaginable distances, it remains visible. That's remarkable. Suppose someone turned on a flashlight in another city. You wouldn't see it. Turn on a lighthouse. Still no. Turn on every light in the city simultaneously? Probably not. Yet gamma-ray bursts remain detectable across distances so large that ordinary comparisons become meaningless. Only truly enormous energies make that possible. And then came events that surprised even experienced astronomers. Occasionally, a burst appears so bright that researchers immediately recognize something unusual has occurred. Instruments become saturated. Data streams spike dramatically. Observatories around the world redirect attention toward the source. For a short period, an entire scientific community focuses on a single explosion occurring billions of light years away. That level of attention isn't given lightly. Astronomers see energetic phenomena regularly. For a gamma-ray burst to stand out among all of them requires something extraordinary. The most famous example arrived recently and would eventually earn a memorable nickname: the boat, the brightest of all time. Even among gamma-ray bursts, some events establish new standards, new records, new benchmarks for power. The boat became one of those moments. Researchers immediately recognized they were witnessing something exceptional. The event generated enormous excitement throughout astronomy. We'll explore that story in detail later. For now, what's important is that even within the category of gamma-ray bursts, nature continues producing surprises. There always seems to be room for something bigger, something brighter, something more energetic, and perhaps that's the most important takeaway. Gamma-ray bursts are not merely powerful explosions, they represent the upper limits of what the universe appears capable of producing. When astronomers ask how energetic a stellar catastrophe can become, gamma-ray bursts provide part of the answer. When they ask how much power can emerge from collapsing stars or colliding neutron stars, gamma-ray bursts provide another answer. These events sit near the extreme edge of known astrophysics, yet understanding their power only solves part of the mystery. The next question is arguably even more interesting. What kind of object can produce an explosion like this in the first place? For most of a star's life, gravity and pressure maintain an uneasy truce. Gravity is always trying to pull everything inward. The immense mass of the star wants to collapse toward the centre. At the same time, nuclear fusion deep inside the core produces enormous amounts of energy. That energy pushes outward. As long as those two forces remain balanced, the star survives. For millions or even billions of years, depending on its mass, the star exists in a state of equilibrium. The arrangement is remarkably stable. Our own Sun has maintained that balance for roughly 4.6 billion years. It will continue doing so for several billion more. Yet not all stars enjoy such long and relatively peaceful lives. Some are born with extraordinary amounts of mass. These stellar giants live fast, burn fuel at astonishing rates, and die spectacularly. And it is within the deaths of these giant stars that many of the universe's most powerful gamma-ray bursts are born. To understand why, we first need to appreciate how different massive stars are from stars like the Sun. Imagine two cars beginning a journey. One drives at a moderate speed and carefully conserves fuel. The other races forward with the accelerator pressed to the floor. The second car covers ground quickly, but it also empties its fuel tank much faster. Massive stars behave in a similar way. The larger the star becomes, the more intense conditions grow inside its core. Higher temperatures increase fusion rates. More fusion produces more energy. More energy means fuel disappears faster. As a result, the bigger stars live surprisingly short lives. A star several times more massive than the Sun might survive only tens of millions of years. That sounds like a long time from a human perspective. In astronomy, however, it is remarkably brief. Some of the most massive stars known may survive only a few million years before reaching the end of their lives. Compared with the Sun's expected lifespan of roughly 10 billion years, that is astonishingly short. Nature rewards mass with power, but charges heavily for the privilege. Throughout its life, a massive star acts like a giant nuclear furnace. Hydrogen fuses into helium. Helium eventually fuses into heavier elements. As the star ages, the fusion process becomes increasingly complex. New layers form. Different elements burn at different depths. The interior starts resembling an onion. Hydrogen in one region, helium in another, carbon deeper inside, oxygen, neon, silicon. The structure grows increasingly elaborate, yet every stage brings the star closer to a critical moment. Eventually, the star begins producing iron. At first glance, that might not sound important. Iron is familiar. We encounter it in buildings, vehicles, tools, and countless everyday objects. Inside a massive star, however, iron represents trouble, a great deal of trouble. The reason involves nuclear physics. Fusion releases energy when lighter elements combine into heavier ones. Hydrogen becomes helium. Helium becomes carbon. The process generates the outward pressure needed to resist gravity. Iron changes the rules. Fusing iron does not release energy. Instead, it consumes energy. The star has reached a dead end. Its primary source of support is disappearing. Imagine a massive suspension bridge suddenly losing the cables holding it up. The structure might remain standing briefly, but collapse becomes inevitable. The same thing happens inside the core of a giant star. For millions of years, fusion has opposed gravity. Then gravity finally gains the upper hand, and when gravity wins inside a massive star, events unfold extraordinarily quickly. The collapse begins, matter rushes inward, the core contracts, temperatures rise, densities increase dramatically. Conditions become almost impossible to imagine. The collapsing core can shrink from a region larger than Earth to something resembling a city in a matter of seconds. That's not a gradual change, that's catastrophe. The speed involved is astonishing. The violence involved is even greater. Imagine compressing an enormous amount of mass into an incredibly small volume. The resulting densities become extreme. A teaspoon of material from these environments could outweigh mountains. Gravity intensifies. Particles collide. Physical processes that rarely matter elsewhere suddenly dominate. Then comes one of the most dramatic moments in stellar evolution. The core collapses so rapidly that it effectively crashes into itself. The inward motion suddenly halts, matter rebounds, a shockwave forms, energy surges outward, the star explodes. Astronomers call this event a core collapse supernova. Even an ordinary core collapse supernova ranks among the most powerful explosions in the universe. For a brief period, the dying star may outshine billions of other stars. Entire galaxies can appear dimmer. The explosion hurls matter into space at tremendous speeds. Heavy elements created during the star's lifetime scatter throughout the surrounding region. Future stars, future planets, future living organisms, all may eventually incorporate material produced by such explosions. In a very real sense, some of the atoms inside your body were forged during ancient stellar deaths. Yet remarkable as supernovae are, they do not automatically produce gamma-ray bursts. Something additional must occur. Something rarer. Something more extreme. For years, astronomers struggled to understand this distinction. Many massive stars die. Only a small fraction generate gamma-ray bursts. Why? The answer appears to involve rotation. Specifically, very rapid rotation. Imagine an ice skater spinning on a rink. When the skater pulls their arms inward, the rotation speeds up. The same basic principle applies during stellar collapse. As the core contracts, rotation can accelerate dramatically. A star that was already spinning rapidly may become extraordinarily fast during collapse. Under the right conditions, the collapsing core forms a black hole. Matter surrounding that newly formed black hole begins falling inward. Not all at once. Instead, much of it forms a rapidly rotating disk. The situation becomes incredibly energetic. Matter spirals toward the black hole. Magnetic fields intensify. Temperatures soar. Enormous amounts of energy become available. And somewhere within this chaos, nature constructs one of its most extraordinary creations, a relativistic jet. These jets emerge from regions near the black hole. They contain matter and energy accelerated to speeds approaching the speed of light. Rather than exploding equally in every direction, the dying star channels tremendous energy into narrow beams. The process resembles placing a nozzle on a fire hose. Instead of water spreading everywhere, it becomes focused into a concentrated stream. The difference is that this particular stream carries enough energy to outshine galaxies. The jet begins forcing its way outward. Remember, the collapsing star hasn't disappeared. The jet must punch through layers of stellar material. This is not an easy task. The star remains enormous, dense, violent. The jet essentially drills a path through the dying star. As it advances, temperatures and pressures remain extreme. Shock waves form. Radiation floods the region. The struggle continues until the jet finally emerges into space. And that's when astronomers can observe a gamma-ray burst. The burst itself is not merely the exploding star, it's the focused beam escaping from that collapsing system. Viewed from the correct angle, the event becomes one of the brightest things in the observable universe. Viewed from another angle, it might remain completely invisible. This realization solved one of the great puzzles surrounding gamma-ray bursts. Scientists eventually understood that many bursts were not fundamentally different in energy. They simply differed in orientation. Some jets pointed toward Earth, others did not. We observe only a small fraction of all the gamma-ray bursts that actually occur. The universe likely produces many more than we detect. Most beams never intersect our location. There's something interesting about that. At any given moment, somewhere in the observable universe, a giant star may be dying. A black hole may be forming. Relativistic jets may be erupting into space. A gamma-ray burst may be racing across billions of light-years. Yet unless the geometry aligns correctly, we remain completely unaware. The cosmos is constantly active. We merely catch occasional glimpses. Scientists eventually gave a name to these especially energetic stellar deaths. Hypernovae. The term sounds dramatic because the phenomenon deserves it. A hypernova represents one of the most extreme endpoints of stellar evolution. Not every massive star becomes a hypernova. Not every hypernova produces a gamma-ray burst. But when the right combination of mass, rotation and collapse occurs, the results are extraordinary. One of the reasons astronomers became confident in this explanation involved afterglows. Remember the afterglows we discussed earlier? Those lingering emissions that continue after the initial burst. As telescopes improved, researchers began tracking afterglows more effectively. Eventually, they noticed something fascinating. In several cases, evidence of a supernova appeared alongside the gamma-ray burst. The connection was becoming impossible to ignore. Again and again, long-duration gamma-ray bursts seemed associated with dying, massive stars. The observations pointed toward the same conclusion. Gamma-ray bursts weren't random. They weren't mysterious flashes with no explanation. They were signatures of stellar death on an unimaginable scale. One particularly important example appeared in 1998. Astronomers studying a gamma-ray burst discovered compelling evidence linking it to a supernova. The connection provided a major breakthrough. Years of speculation suddenly had observational support. Theoretical predictions and actual data were beginning to align. Scientists love moments like that. A hypothesis survives contact with reality. Confidence grows. Understanding deepens. More observations followed. More connections emerged. The evidence accumulated steadily. Today, the relationship between long-duration gamma-ray bursts and collapsing massive stars stands as one of the major successes of modern astrophysics. Yet the story remains astonishing. Think about what we're actually describing. A star many times larger than the Sun spends millions of years fusing elements in its core. Eventually it exhausts its fuel. Gravity overwhelms internal pressure. The core collapses. A black hole forms. Matter spirals inward. Relativistic jets erupt outward. The jets punch through the star. Gamma rays flood into space. And for a few seconds, the event becomes one of the brightest phenomena in existence. All of that unfolds because a giant star reaches the end of its life. There's another fascinating aspect to consider. These stars help shape the universe around them. Massive stars are rare compared with smaller stars. Yet their influence is enormous. They manufacture heavy elements. They enrich galaxies. They trigger new waves of star formation. And when they die, they transform their surroundings. Gamma-ray bursts represent one of the most dramatic examples of that influence. The effects extend far beyond the original star. Shock waves propagate through space. Material disperses into interstellar clouds. Future generations of stars inherit the aftermath. The cycle continues. In some cases, astronomers have observed gamma-ray bursts originating billions of light-years away. That means the stars responsible died when the universe was much younger. long before Earth existed, long before the solar system formed. The bursts we observe today often began their journeys during ancient epochs of cosmic history. Their light has travelled across expanding space ever since. There's something remarkable about receiving that information now. A star dies in a distant galaxy. Its final moments create one of the most powerful explosions known. Billions of years later, scientists on a small rocky planet detect the signal and reconstruct the story. The event itself is gone. The information remains, and that's one of the beautiful aspects of astronomy. Light allows us to investigate events long after they occur. Gamma-ray bursts become records of ancient catastrophes, messages carried across time, evidence preserved within radiation. Not every gamma-ray burst begins with the death of a giant star. That realization took astronomers quite a while to fully appreciate. For years, researchers suspected a single explanation might account for all gamma-ray bursts. The idea seemed reasonable. After all, every burst involved tremendous energy. Every burst produced intense gamma radiation. Every burst appeared capable of extraordinary luminosity. Perhaps one mechanism simply produced different variations of the same phenomenon. The universe had other ideas. As observations improved, astronomers noticed patterns that refused to fit neatly into a single category. Some bursts lasted many seconds. Others ended almost immediately. Some appeared associated with regions where massive stars were actively forming. Others appeared in places where very few young stars existed. Some occurred in galaxies bustling with stellar birth. Others appeared in older galaxies where star formation had largely slowed down. The clues were accumulating. Eventually, the evidence became impossible to ignore. Long-duration gamma-ray bursts and short-duration gamma-ray bursts were not identical events. They had different origins, different histories, different cosmic stories, and if long bursts often marked the deaths of giant stars, short bursts appeared to emerge from something equally dramatic but fundamentally different. Instead of witnessing the collapse of a living star, astronomers were watching the collision of dead ones. Not ordinary dead stars, neutron stars, among the strangest objects in the entire universe. To understand why their collisions produce gamma-ray bursts, we first need to understand what a neutron star actually is. Imagine a star significantly larger than the Sun. Not large enough to create the most powerful long-duration gamma-ray bursts we discussed earlier, but still massive enough to end its life in a supernova explosion. When that star dies, gravity crushes the remaining core. The collapse becomes so intense that atoms themselves cease to function normally. Electrons and protons combine. Matter is compressed to extraordinary densities. The result is an object composed primarily of neutrons, hence the name, neutron star. The numbers involved are difficult to comprehend. A typical neutron star may contain more mass than the Sun, yet all that mass becomes squeezed into a sphere only about 20 kilometers across. Imagine compressing the Sun into a region roughly the size of a city. The density becomes almost absurd. Astronomers often use the famous teaspoon comparison. A teaspoon of neutron star material would weigh billions of tons on Earth. That's not an exaggeration. It's simply what happens when matter is compressed to such extraordinary extremes. Gravity becomes immense. Conditions become unlike anything we encounter in everyday life. A neutron star occupies a peculiar middle ground between ordinary stars and black holes. It isn't large. It isn't bright in the traditional sense, yet it contains enormous mass concentrated into a tiny volume. If you stood on the surface of a neutron star, assuming such a thing was somehow possible, the gravitational environment would be unimaginably hostile. Fortunately, nobody is planning a vacation there. The object would not be particularly welcoming. Many neutron stars exist alone. Some spin rapidly, producing beams of radiation that sweep through space. These are known as pulsars. Others remain relatively quiet. Yet some neutron stars are not solitary. Some exist in binary systems. Two neutron stars orbiting one another. At first glance, this might sound stable. After all, stars orbit each other throughout the universe. Binary systems are common. The difference lies in gravity. Neutron stars possess enormous mass packed into incredibly small regions. As they orbit one another, something important happens. They begin losing energy. Einstein predicted this long before anyone directly observed neutron star mergers. According to general relativity, accelerating masses create ripples in space-time known as gravitational waves. These waves carry energy away from the system. The effect is usually tiny. For neutron stars, however, it becomes significant over long periods. The stars gradually spiral inward. Not quickly, not dramatically at first. The process can take millions or even billions of years. Imagine two figure skaters holding hands while slowly rotating. If they move closer together, their motion changes. The same basic idea applies here, although the physics is far more extreme. The orbit shrinks, the stars move closer, the dance accelerates. Over vast stretches of time, the neutron stars approach each other relentlessly. Then things become interesting, very interesting. As the distance decreases, the orbital speed increases. The stars begin circling each other faster and faster. Minutes become seconds. Seconds become fractions of seconds. Eventually, the two neutron stars are racing around each other hundreds of times every minute. The system enters its final moments. Gravity dominates everything. Space-time itself becomes severely distorted. The stars draw closer, closer, closer still, and then they collide. When astronomers use the word collision here, it may create the wrong mental image. This isn't like two cars meeting at an intersection, nor is it like two planets gently merging. We're talking about objects containing enormous amounts of mass, objects moving at tremendous speeds, objects existing under some of the most extreme physical conditions in the cosmos. The merger releases staggering amounts of energy. Matter becomes violently disrupted. Magnetic fields intensify. Temperatures soar. Shock waves race outward. The entire event unfolds with extraordinary violence. For a brief period, conditions become so energetic that a short-duration gamma-ray burst can emerge. The burst itself is typically much shorter than those associated with collapsing giant stars. Many last less than 2 seconds. Some last only fractions of a second. Yet despite their brevity, they remain among the most powerful explosions known. It's one of the recurring themes of gamma-ray bursts. The universe accomplishes astonishing things very quickly. A neutron star merger may take billions of years to arrange. The final collision happens in moments. The resulting gamma-ray burst may last only seconds. Yet the energy released rivals some of the most dramatic events in existence. For many years, astronomers suspected neutron star mergers were responsible for short-duration bursts. The theory made sense. The physics worked. The observations were suggestive. Still, suspicion is not proof. Scientists wanted direct evidence. They wanted confirmation, and eventually they got it. The breakthrough arrived in 2017. It became one of the most important moments in modern astronomy. To appreciate why, we need to briefly discuss gravitational waves. For more than a century, gravitational waves remained a prediction of Einstein's theory. Researchers believed they existed. Mathematics strongly supported their existence. Yet direct detection proved extraordinarily difficult. The distortions they create are incredibly small. Detecting them requires astonishing precision. Eventually, facilities such as LIGO succeeded. Humanity gained the ability to observe ripples in space-time itself. That achievement was already revolutionary. Then something even more remarkable happened. On August 17, 2017, gravitational wave detectors recorded a signal. The pattern indicated two neutron stars spiraling together and merging. At almost exactly the same time, space-based instruments detected a short gamma-ray burst. Suddenly, two completely different forms of observation were pointing toward the same event. Astronomers around the world immediately became excited. Telescopes were redirected, observatories began searching the region, and they found it. For the first time, scientists observed a neutron star merger through gravitational waves and electromagnetic radiation simultaneously. The event became known as GW170817. It represented a historic milestone. For decades, researchers had suspected neutron star mergers created short-duration gamma-ray bursts. Now they had direct evidence. The case became dramatically stronger. One of the most fascinating aspects of the discovery involved what happened afterward. Astronomers observed an unusual glow, not merely an afterglow from the gamma-ray burst, something additional. The observations matched predictions for an event called a kilonova. A kilonova occurs when neutron-rich material ejected during a merger undergoes radioactive decay. The resulting glow can become extraordinarily bright. More importantly, it provides evidence for something profound: the creation of heavy elements. This brings us to one of the most remarkable consequences of neutron star collisions: gold, platinum, uranium. Many of the heaviest elements in the periodic table require environments of extraordinary intensity. For years, scientists debated exactly where those elements originated. Neutron star mergers appear to provide a major part of the answer. During the collision, conditions become extreme enough for rapid neutron capture processes to occur. Atomic nuclei absorb neutrons at astonishing rates. Heavy elements form, then they are scattered into space. The implications are extraordinary. Consider a gold ring. Perhaps one worn by a friend, a family member, or maybe one resting in a jewelry store display. The gold inside that ring may owe its existence to a neutron star collision that occurred billions of years ago. Two dead stars spiraled together. They merged in a catastrophic explosion. Heavy elements formed. Those elements eventually became incorporated into future generations of stars and planets. And much later, humans mined the material and shaped it into jewelry. That's quite a journey. It's one of the most remarkable examples of cosmic recycling. The universe wastes very little. Matter constantly changes form. Stars create elements. Explosions distribute them. New stars emerge. Planets form. Life appears. The cycle continues. Neutron star mergers play a critical role in that process. Their influence extends far beyond the gamma-ray bursts they produce. Another interesting difference between giant star collapses and neutron star mergers involves environment. Long-duration bursts often occur in regions rich with young stars. That makes sense. Massive stars live relatively short lives. They die near the places where they formed. Neutron stars behave differently. They can survive for billions of years before merging. During that time, they may travel significant distances. As a result, short-duration gamma-ray bursts sometimes occur far from active star-forming regions. This distinction helped astronomers identify the different origins of the two burst categories. The clues were hiding in the locations all along. The universe was providing hints. Researchers simply needed enough data to recognize them. One aspect of neutron star mergers continues to fascinate scientists. These events represent laboratories for physics under conditions impossible to reproduce on Earth. Extreme gravity, extreme density, extreme magnetic fields, extreme energy. The merger creates a natural experiment operating at scales far beyond anything human technology can achieve. By studying these collisions, researchers learn about matter itself, how it behaves, how it changes, how the laws of physics function under extraordinary circumstances. In this sense, gamma-ray bursts are not merely explosions, they are opportunities, windows into environments otherwise inaccessible. Every observation teaches us something. Every burst adds another piece to the puzzle, and despite all we've learned, important questions remain. Exactly how are the jets launched? What determines their structure? Why do some bursts appear stronger than others? What happens immediately after the merger? Astronomers continue searching for answers. The story is far from complete. Still, one conclusion has become clear. Short-duration gamma-ray bursts are among the most dramatic consequences of neutron-star collisions. They mark the violent union of some of the densest objects in existence. They generate immense energies. They create heavy elements. They reshape their surroundings. And for a brief instant, they produce flashes detectable across vast regions of the universe. One of the most surprising discoveries in gamma-ray burst research arrived after astronomers had already accepted that these events were among the most powerful explosions in the universe. At first, the numbers seemed almost unbelievable. Researchers calculated the energy outputs, they estimated distances, they measured brightness, and the results looked absurdly large. Some gamma-ray bursts appeared capable of releasing more energy than scientists thought physically reasonable. That immediately raised concerns, not because the observations were necessarily wrong, but because nature generally prefers efficiency. Whenever calculations produce truly extreme values, astronomers begin asking whether something important has been overlooked. In the case of gamma-ray bursts, something had indeed been overlooked. The explosions were not behaving like ordinary light bulbs, they were behaving more like cosmic searchlights, and that realization transformed our understanding of the entire phenomenon. To appreciate why, let's imagine two people trying to illuminate a field at night. The first person holds a lantern. The lantern sends light outward in every direction. Some light travels upward, some downward, some sideways. The energy spreads broadly across the surrounding environment. The second person carries a powerful flashlight. The total energy may be similar, but instead of spreading everywhere, the flashlight concentrates most of its energy into a narrow beam. If you're standing directly in front of the flashlight, it appears dramatically brighter than the lantern. The energy has been focused, directed, concentrated. This simple difference turns out to be enormously important. For many years, astronomers assumed gamma-ray bursts radiated energy equally in all directions. That assumption seemed reasonable. Many astronomical objects behave that way. Stars shine in every direction. Most supernovae expand outward in roughly spherical patterns. Countless cosmic processes distribute energy relatively evenly. Gamma-ray bursts appeared different. As researchers gathered more observations, evidence accumulated that these explosions were not spherical at all. Instead, they were producing narrow jets, enormously powerful jets capable of carrying extraordinary amounts of energy across vast distances. Once scientists accounted for this effect, the puzzle began making sense. The burst remained incredibly powerful, but they no longer required impossible amounts of energy. Nature had found a clever solution. Instead of illuminating the entire universe equally, it concentrated energy into narrow beams. It's the difference between trying to light an entire city and aiming a laser pointer at a specific target. Focus changes everything. Of course, that raises an obvious question. Why do these jets form in the first place? The answer lies in some of the most extreme environments known to science. Whether we're discussing a collapsing giant star or a neutron star merger, the central engine responsible for a gamma-ray burst operates under extraordinary conditions. Matter spirals inward. Magnetic fields become intensely powerful. Rotation reaches incredible speeds. Gravity dominates the surrounding region. These ingredients combine to create structures that naturally channel energy along specific directions. Imagine water rushing toward a drain. The flow becomes organized, directed, concentrated. Now imagine a cosmic version involving black holes, magnetic fields, and matter moving at nearly the speed of light. The result can be a relativistic jet. The term relativistic is important here. Astronomers use it when objects move fast enough for Einstein's theory of relativity to become significant. Gamma-ray burst jets don't merely travel quickly, they travel astonishingly quickly, often more than 99.99% of the speed of light. At such velocities, reality begins behaving in ways that differ dramatically from everyday experience. Energy becomes concentrated, Time behaves differently for moving particles. Radiation becomes strongly focused in the direction of motion. These effects contribute directly to the incredible brightness observed from Earth. Suppose one of these jets points almost directly toward us. The concentrated radiation reaches our detectors. The burst appears extraordinarily bright, perhaps bright enough to outshine a galaxy, perhaps bright enough to become detectable across billions of light years. Meanwhile, an observer located elsewhere might see something entirely different, or nothing at all. This realization solved another major mystery. For years, astronomers wondered whether gamma-ray bursts were genuinely rare. The observed numbers seemed relatively modest. Considering the size of the universe, researchers expected more. Then they recognized the importance of jet orientation. Imagine standing in a dark field while hundreds of lighthouses rotate in the distance. You only notice a lighthouse when its beam sweeps across your position. The lighthouse shines continuously. Your awareness depends entirely on geometry. Gamma-ray bursts work similarly. The universe may produce many more bursts than we observe. Most simply never point toward Earth. We see the fortunate alignments. The rest remain hidden. That idea carries fascinating implications. At this very moment, somewhere in the observable universe, multiple gamma-ray bursts may be occurring. Stars may be collapsing. Neutron stars may be merging. Relativistic jets may be racing into space. Yet unless one of those beams intersect our location, we remain unaware. The cosmos is probably far more active than our observations suggest. We're seeing only a fraction of the activity. Astronomers sometimes compare this situation to fishing with a very narrow net. You catch some fish, you know others escaped. The challenge is estimating how many. Researchers have spent years trying to determine how many gamma-ray bursts occur for every one we detect. The answer remains uncertain. However, the true number almost certainly exceeds the observed number substantially. Geometry hides many events from view. Another consequence involves brightness estimates. Suppose you observe a flashlight from directly in front of its beam. Without understanding the flashlight's design, you might assume the light spreads equally in all directions. You would then overestimate the total energy being produced. The same thing initially happened with gamma-ray bursts. Early calculations assumed isotropic emission. In other words, equal emission in every direction. Once astronomers recognized the presence of jets, energy estimates could be adjusted accordingly. The bursts remained among the most energetic events known, but the corrected values became more physically plausible. This represented an important scientific advance, not because gamma-ray bursts became less impressive. They didn't. The explosions remained extraordinary. Instead, researchers gained a more accurate understanding of how nature was producing such remarkable brightness. Interestingly, the jets themselves remain subjects of active research. Scientists know they exist. Observations strongly support their presence, yet many details remain uncertain. How exactly are the jets launched? What determines their shape? Why are some narrower than others? What role do magnetic fields play? These questions continue driving research today. The physics involved is exceptionally challenging. Conditions near black holes and neutron star mergers are difficult to model. Matter behaves in unusual ways. Magnetic fields become incredibly intense. Relativity influences everything. Creating accurate simulations requires enormous computational power. Fortunately, modern astronomy possesses increasingly sophisticated tools. Researchers now build detailed computer models capable of recreating many aspects of jet formation. These simulations help explain observations and generate predictions. Sometimes the models succeed brilliantly, other times the universe reveals something unexpected. That's part of the fun. Nature rarely feels obligated to follow our assumptions. One especially fascinating aspect of relativistic jets involves something called relativistic beaming. The name sounds technical. The underlying concept is surprisingly intuitive. Imagine riding a bicycle through rain. When stationary, raindrops fall from many directions. Once you start moving, the rain appears concentrated toward the front. Your motion changes how you experience the environment. Something similar happens with radiation emitted by material moving near the speed of light. The radiation becomes concentrated in the direction of motion. Observers located within that beam receive an amplified signal. Observers outside the beam receive much less. This effect contributes significantly to the extraordinary brightness of gamma-ray bursts. It's not merely that the explosions are powerful, it's also that the emitted radiation becomes focused, concentrated, directed towards specific regions of space. The combination is remarkable. High energy plus strong beaming equals extraordinary visibility. Another clue supporting the jet model comes from afterglows. As gamma-ray burst afterglows evolve, astronomers sometimes observe characteristic changes in brightness. The light fades in a particular way. These patterns often match predictions associated with expanding jets. It's rather like watching a flashlight beam gradually spread out. The geometry influences what observers see. Careful analysis of afterglows helped strengthen the case for narrow jets. Evidence accumulated from multiple directions, theoretical models, observational data, computer simulations. Everything pointed toward the same conclusion. Gamma-ray bursts are highly focused events. The implications extend beyond simple brightness calculations. Jet orientation can also influence what kind of event astronomers believe they're observing. Suppose a burst points directly toward Earth. The signal appears exceptionally bright. The gamma rays dominate the observation. Now imagine viewing the same event from a different angle. The gamma ray signal might be weaker, perhaps even undetectable, yet other emissions could remain visible. The same underlying catastrophe might look completely different depending on perspective. Astronomy occasionally encounters this phenomenon. Objects are not always what they seem. Sometimes observation angle matters enormously. Gamma-ray bursts provide a striking example. Researchers increasingly suspect that many apparently different cosmic events may actually represent similar phenomena viewed from different directions. The universe does not always change. Sometimes our perspective changes. One particularly important demonstration arrived during studies of neutron star mergers. The famous event GW 170817 produced a gamma-ray burst that appeared somewhat unusual. Initially, astronomers were puzzled. The burst seemed weaker than expected. Later analysis suggested a simple explanation. The jet was not pointed directly toward Earth. Instead, observers were viewing the event slightly off-axis. That subtle difference changed the appearance dramatically. The discovery reinforced how important geometry can be. Even among the most powerful explosions in existence, viewing angle matters a lot. This realization also helps explain why detecting gamma-ray bursts requires a degree of luck. The universe can produce a spectacular explosion. The energy can be enormous. The event can reshape its local environment. Yet if the jet points elsewhere, Earth-based observers may never notice. The burst effectively misses us. Billions of years later, nobody on Earth knows it happened. That's a curious thought. History is full of events we never witnessed. The cosmos is no different. Countless extraordinary occurrences have unfolded beyond our awareness. Gamma-ray bursts remind us of that fact. Our observations reveal only part of reality. There's always more happening beyond the limits of our perspective. The jets themselves also create some of the fastest moving material known. When scientists describe matter travelling at 99.99% of the speed of light, it becomes difficult to maintain ordinary intuition. At such speeds, the distinction between everyday experience and relativistic physics becomes enormous. Time dilation becomes important. Energy increases dramatically. The behaviour of radiation changes. Gamma-ray burst jets operate in this extraordinary regime. They provide natural laboratories for studying physics under conditions impossible to reproduce on Earth. No human-built machine approaches these scales. Particle accelerators are remarkable achievements. Nature remains considerably more ambitious. A collapsing star or neutron star merger can accelerate matter to energies that challenge our best technology. Every gamma-ray burst therefore offers an opportunity to learn about relativistic physics, magnetic fields, extreme gravity, high-energy particle interactions. The bursts are not merely explosions, they're experiments conducted by the universe itself. Experiments occurring billions of light-years away, experiments we can observe only because the resulting beams cross unimaginable distances, and cross those distances they certainly do. Some gamma-ray bursts originate so far away that their light began travelling toward Earth when the universe was only a fraction of its current age. The jets carry information across billions of years. Eventually a detector captures the signal, a brief spike appears in the data, and astronomers begin reconstructing a story that started long before Earth looked anything like it does today. That's one of the remarkable things about gamma-ray bursts. The beams do more than transport energy. They transport history. Each burst represents a message from another era, a record of conditions existing billions of years ago, a clue about how stars lived and died in distant galaxies, a glimpse into the evolving universe. And because these beams travel such extraordinary distances, they allow astronomers to investigate some of the earliest periods of cosmic history. In fact, some gamma-ray bursts have become among the most distant objects ever detected. Their light has crossed so much space and time that observing them is almost like looking into the universe's childhood. If these bursts can be seen from such incredible distances, just how far have some of them travelled before reaching us? And what can those ancient flashes teach us about the early history of the cosmos itself? Distance in everyday life is usually something we can imagine. A walk to a nearby shop, a drive across town, a flight to another country. Even the longest journeys most of us experience remain comfortably within the scale of a single planet. Astronomy quickly abandons those familiar measurements. The Moon sits approximately 384,000 kilometers from Earth. That already sounds enormous, yet sunlight covers that distance in just over a second. The Sun, by comparison, lies about 150 million kilometers away. Light requires roughly 8 minutes to make the journey. Those numbers seem impressive until we leave the solar system entirely. The nearest star beyond the Sun, Proxima Centauri, sits more than 4 light-years away. A light-year is the distance light travels in 1 year, not 1 hour, not 1 day, 1 year. Even moving at the fastest speed allowed by the laws of physics, a signal still needs more than 4 years to travel between those stars. Suddenly the solar system begins to feel much smaller than it once did. Then we encounter the Milky Way. Our galaxy stretches roughly 100,000 light-years across. Light can circle Earth 7.5 times in a single second. Even at that incredible speed, crossing the Milky Way would require 100,000 years. The scale is difficult to grasp, yet galaxies themselves are merely components of something larger. The observable universe contains hundreds of billions of galaxies. Some are relatively nearby, others are staggeringly distant, and it is within those distant galaxies that many gamma-ray bursts occur. One of the reasons astronomers find gamma-ray bursts so fascinating is that they can be detected across extraordinary distances. These explosions are so luminous that they remain visible long after their light has crossed billions of light-years of expanding space. That fact alone is remarkable. Imagine standing on one side of a continent and somehow seeing a single candle burning on the opposite side. Impossible, of course. The candle's light would disperse long before reaching you. Gamma-ray bursts overcome similar challenges on scales so vast that ordinary comparisons break down. They remain visible not across continents, but across enormous fractions of the observable universe. In some cases, the photons arriving at our detectors began their journey billions of years before Earth even existed. That means every time astronomers observe one of these ancient bursts, they are effectively receiving a message from the distant past. Not a deliberate message, a The universe isn't writing letters. Still, information is travelling across time. The light reaching Earth today tells us about conditions that existed long ago. This idea lies at the heart of modern astronomy. When you look at the moon, you're seeing it as it appeared about 1.3 seconds ago. When you look at the sun, you're seeing it as it was 8 minutes ago. Observe a star 1,000 light-years away, and you're seeing light that left before many of the events recorded in human history. Astronomy is fundamentally an exercise in looking backward through time. The farther away an object is, the older the information becomes. Gamma-ray bursts take this principle to extraordinary extremes. Some of the most distant bursts ever observed originated when the universe was still very young. Their light has spent billions of years travelling toward us. Entire geological eras passed on Earth during that journey. Species evolved, continents shifted, civilizations emerged, languages developed. Empires rose and fell, and all the while those photons continued racing through space. Eventually, after crossing unimaginable distances, they reached a detector orbiting our planet. There's something astonishing about that. A star dies in a galaxy so distant that its light requires billions of years to arrive. Then one day, a computer registers a brief signal. A spike appears in the data, and scientists realize they're observing an event that happened before Earth looked anything like it does now. In a sense, gamma-ray bursts function as time machines, not the science fiction variety. No one travels anywhere. No one changes history. Yet these bursts allow us to observe ancient epochs directly. They provide information from eras that would otherwise remain difficult to study. This becomes especially important when we consider the early universe. The first stars formed hundreds of millions of years after the Big Bang. Galaxies gradually assembled. Heavy elements became more abundant. Structure emerged. Astronomers would love to observe those periods in detail. The problem is distance. The farther back we look, the fainter objects become. Many ancient galaxies are incredibly difficult to study. Gamma-ray bursts help solve part of that problem. Because they are so bright, they can remain visible even when originating from enormous distances. For a brief period, they become cosmic beacons, lighthouses shining across billions of years. And just as sailors can learn about a coastline by studying a lighthouse beam, astronomers can learn about the early universe by studying gamma-ray bursts. One particularly useful feature involves the journey itself. The light from a distant burst doesn't travel through empty nothingness. Intergalactic space may be sparse, but it isn't completely devoid of matter. Gas clouds exist. Galaxies exist. Various forms of material lie scattered throughout the cosmos. As gamma-ray burst light passes through these regions, interactions occur. Specific wavelengths may be absorbed, others may pass through. The resulting patterns become encoded within the arriving light. Astronomers can analyze those patterns. Doing so allows them to investigate environments located billions of light-years away. In some cases, researchers learn about ancient gas clouds that would otherwise remain nearly invisible. In other cases, they study the chemical composition of distant galaxies. The burst itself becomes a flashlight illuminating whatever lies between the source and Earth. It's a remarkably useful arrangement. The universe provides both the light source and the laboratory. Scientists simply need to interpret the results. Several gamma-ray bursts have established distance records over the years. Each discovery pushed observations farther into cosmic history. Each revealed conditions existing earlier in the universe's evolution. Among the most famous examples was GRB 090423. Detected in 2009, the burst originated from an extraordinarily distant location. Measurements indicated the event occurred when the universe was only about 630 million years old. To put that in perspective, the universe today is approximately 13.8 billion years old. This burst came from a time when the cosmos had experienced less than 5% of its current history. Human beings did not exist. Earth did not exist. The sun did not exist, yet the light survived. For more than 13 billion years, it travelled through expanding space before reaching our instruments. Astronomers were effectively observing a stellar death from the universe's childhood. That is an extraordinary achievement. Another reason distant gamma-ray bursts attract so much attention involves star formation. The early universe looked very different from the modern cosmos. Galaxies were smaller. Chemical abundances differed. Stars formed under conditions unlike those we observe today. By studying ancient gamma-ray bursts, researchers gain insights into those environments. Every burst provides another clue. Every observation adds another piece to the historical record. It's a little like archaeology. Except instead of digging into ancient soil, astronomers analyze ancient light. The principle remains surprisingly similar. Both disciplines reconstruct the past using surviving evidence. Gamma-ray bursts simply provide evidence on a cosmic scale. Of course, observing events at such distances introduces challenges. The universe expands. This expansion affects the light travelling through it. Wavelengths stretch. Colours shift. Astronomers call this phenomenon redshift. The greater the distance, the greater the redshift tends to become. Think of it as a kind of cosmic fingerprint. By measuring redshift, researchers estimate how far away an object is and how long its light has been travelling. Gamma-ray bursts often exhibit substantial redshifts. That immediately tells astronomers they're observing something ancient and distant. Some bursts effectively serve as markers placed throughout cosmic history. By comparing events from different eras, scientists learn how stars and galaxies evolved over time. The bursts become chapters in a story spanning billions of years. One fascinating aspect of this work is that the universe itself acts as an archive. Human records rarely survive more than a few thousand years. Ancient civilizations left monuments and texts. Those are precious historical resources. Yet compared with cosmic history, they represent only brief moments. Gamma-ray bursts allow us to investigate events occurring billions of years ago. The archive extends almost unimaginably far into the past, and unlike written records, the information arrives directly from the event itself. No intermediaries, no storytellers, just photons carrying evidence across time. Another interesting consequence emerges when we think about the life cycle of stars. Many of the gamma-ray bursts reaching Earth today originated from stars that died billions of years ago. The galaxies containing those stars may look completely different now. Some may have merged with other galaxies, others may have continued evolving for billions of years. The original environments no longer exist in the form we observe, yet the light preserves a snapshot, a frozen moment from long ago. Astronomy frequently works this way. When we observe distant objects, we aren't seeing what they look like right now. We're seeing historical versions. The farther away an object becomes, the older the snapshot. Gamma-ray bursts simply extend this principle to extraordinary distances. Researchers sometimes describe them as probes of the distant universe. That's an excellent description. The bursts provide information from places and times otherwise difficult to access. They help astronomers investigate ancient star formation, ancient galaxies, ancient chemical environments, ancient cosmic conditions, and because gamma-ray bursts are so bright, they can remain useful even when originating from tremendous distances. There are limits, of course. Eventually objects become too faint, observations become more difficult. Yet gamma-ray bursts continue pushing those boundaries. Again and again, they reveal information from increasingly remote eras. Every new record expands our view of cosmic history. It's worth pausing for a moment to appreciate how remarkable that is. A giant star dies, or two neutron stars collide. An explosion occurs. For a few seconds, the event becomes one of the brightest things in the observable universe. Then the light begins a journey lasting billions of years, long after the original star has vanished, long after its galaxy has evolved. The signal remains in transit. Eventually it arrives here, a detector captures it. Scientists analyze it, and humanity learns something about a period of history otherwise inaccessible. Few astronomical phenomena provide that combination of power and utility. Gamma-ray bursts are simultaneously fascinating objects and valuable scientific tools. They reveal their own origins while also illuminating the universe around them. The farther away the burst, the farther back in time we can look. Yet distance introduces another thought-provoking possibility. If these explosions are powerful enough to remain visible across billions of light years, what would happen if one occurred much closer? The answer is not entirely comforting, because while most gamma-ray bursts pose absolutely no threat to Earth, a sufficiently nearby burst could have significant consequences for a planet unfortunate enough to sit in its path. What would happen if one of these cosmic catastrophes actually struck a world like our own? For most of this journey, gamma-ray bursts have existed at a comfortable distance, billions of light years away, ancient explosions occurring in remote galaxies. Interesting, powerful, perhaps even awe-inspiring, but safely separated from us by vast stretches of space. That distance matters a lot. Whenever astronomers discuss cosmic dangers, distance is usually the first thing they consider. The universe contains many violent phenomena. Supernovae explode, black holes consume matter, stars erupt, galaxies collide. Yet most of these events pose no threat whatsoever, because they happen unimaginably far away. Distance is one of the greatest protective factors in astronomy. Even an extraordinarily powerful event becomes harmless when it occurs far enough away. A campfire can warm your hands. A forest fire can devastate a landscape. The sun produces enough energy to sustain life on Earth. Move the same sun a few light years away, however, and it becomes just another star in the night sky. Power alone does not determine danger. Distance matters just as much, possibly more. So when people ask whether gamma-ray bursts are dangerous, astronomers usually begin with reassuring news. The overwhelming majority of gamma-ray bursts occur so far away that they cannot affect Earth in any meaningful way. Most originate in distant galaxies. Many occur billions of light years from our planet. By the time their radiation reaches us, the energy is spread across enormous volumes of space. What remains is sufficient for scientific instruments to detect, but not enough to cause harm. In practical terms, those bursts are fascinating research opportunities rather than threats. Still, the question remains, what if one occurred nearby? Not next door necessarily, just close enough for its beam to intersect a planet. What would actually happen? The answer turns out to be both interesting and slightly unsettling. To understand why, we need to remember what makes gamma-ray bursts unusual. These events release enormous amounts of energy. More importantly, much of that energy emerges as high-energy radiation. Gamma rays occupy the most energetic end of the electromagnetic spectrum. Unlike visible light, they possess enough energy to disrupt atoms and molecules. They can break chemical bonds. They can alter biological tissues. They can trigger complex reactions in planetary atmospheres. This doesn't mean every gamma ray is automatically catastrophic. Earth encounters various forms of radiation constantly. The atmosphere protects us remarkably well. The problem arises when the amount of incoming radiation becomes extreme. A sufficiently nearby gamma ray burst could deliver exactly that. Notice the phrase, sufficiently nearby. Astronomers are not talking about something occurring in another galaxy. The burst would need to be relatively close by cosmic standards. Fortunately, space is enormous, and such events are rare. Unfortunately, rare does not mean impossible. Scientists have therefore spent considerable time investigating the consequences. The results are fascinating, and occasionally a little alarming. Let's imagine a hypothetical scenario. A gamma-ray burst occurs somewhere within our own galaxy. Not close enough to vaporize Earth, not close enough to physically disrupt the solar system, simply close enough for one of its relativistic jets to point directly at our planet. The first thing to understand is that people on Earth probably wouldn't see an approaching beam. Gamma rays are invisible. There would be no dramatic warning in the sky, no glowing signal, no giant cosmic spotlight announcing its arrival. The radiation would simply arrive. If advanced instruments existed at the time, scientists might detect it first. Without technology, the event would initially be completely unnoticed. Yet the atmosphere would notice immediately. Earth's atmosphere is one of the greatest protective systems life has ever possessed. It shields us from ultraviolet radiation. It absorbs many forms of cosmic radiation. It helps regulate temperature. Life depends upon it. A powerful gamma-ray burst would interact directly with that atmosphere. The incoming radiation would not simply pass through unchanged. Instead, it would collide with atmospheric molecules. Those collisions would trigger a cascade of chemical reactions. Nitrogen molecules would break apart. Oxygen chemistry would change. New compounds would form. The atmosphere would begin undergoing substantial alterations. One of the most important consequences involves ozone. Most people know the ozone layer serves as a protective shield against harmful ultraviolet radiation from the sun. Without it, Earth's surface would become a far more hostile environment. A strong enough gamma-ray burst could significantly damage that shield. The process isn't instantaneous. The atmosphere wouldn't suddenly disappear. Instead, complex chemical reactions would gradually deplete ozone concentrations. The result could be substantial thinning of the protective layer. That might not sound particularly dramatic at first. After all, ozone depletion is not as visually impressive as exploding planets. Yet the biological consequences could be profound. With less ozone available, more ultraviolet radiation from the sun would reach Earth's surface. Plants could suffer damage. Marine ecosystems could be affected. Organisms exposed to increased ultraviolet levels would face additional stress. Food chains could experience disruptions. The effects would ripple through entire ecosystems. Interestingly, many scientists believe the atmosphere itself would absorb most of the direct gamma-ray radiation. That's actually good news. The atmosphere acts like a giant shield. Without it, the situation would be far worse. The bad news is that the shielding process creates secondary consequences. The atmosphere protects life, but it pays a price while doing so. Imagine a castle wall stopping an invading force. The wall succeeds, the city survives, yet the wall itself may suffer substantial damage during the defense. Earth's atmosphere behaves similarly. It protects the surface, but significant atmospheric changes can result. Some researchers have suggested that gamma-ray bursts might even contribute to mass extinction events under certain circumstances. Notice the careful wording. Might. Scientists are cautious here. Direct evidence remains difficult to obtain. The fossil record is incomplete. Ancient atmospheric conditions are not always easy to reconstruct. Nevertheless, the possibility has attracted serious attention. One famous hypothesis involves the Ordovician-Silurian extinction event. This extinction occurred approximately 443 million years ago. At the time, life existed primarily in the oceans. A substantial fraction of species disappeared. The exact causes remain debated. Climate change likely played an important role. Glaciation appears significant. Yet some researchers have wondered whether a gamma-ray burst might have contributed. The idea is not that the burst instantly exterminated life. Instead, atmospheric disruption could have weakened ecosystems, making them more vulnerable to other stresses. Again, this remains speculative. No one can prove a gamma-ray burst caused that extinction. The hypothesis simply illustrates the kind of influence such an event might exert. It's a reminder that cosmic phenomena occasionally affect planetary environments. Earth does not exist in isolation. Our planet occupies a larger cosmic ecosystem. Most of the time, that ecosystem behaves quite peacefully. Occasionally, however, the universe reminds us that it can be energetic, very energetic. Another interesting consequence involves geography. A gamma-ray burst would not necessarily affect every part of a planet equally. The side facing the incoming radiation would receive the strongest exposure. Atmospheric effects could vary by latitude. Climate responses might differ from region to region. The exact outcome would depend upon numerous factors: distance, burst intensity, atmospheric composition, planetary rotation, magnetic field strength. The complexity makes precise predictions challenging. Scientists therefore rely heavily on computer simulations. Fortunately, modern simulations have become increasingly sophisticated. Researchers can model atmospheric chemistry. They can estimate ozone depletion. They can investigate ecological consequences. These studies provide valuable insights into planetary vulnerability. They also help identify safe distances. This brings us to an encouraging point. Gamma-ray bursts are extraordinarily powerful. They are not infinitely powerful. Distance still matters enormously. A burst occurring several billion light-years away poses essentially no danger. A burst occurring thousands of light-years away might still be harmless depending on orientation and intensity. Only a relatively nearby event aligned correctly would become concerning. The combination of factors required is uncommon, very uncommon. Astronomers spend a great deal of time calculating probabilities. People naturally want to know the risk. How likely is Earth to experience such an event? The answer appears reassuring. Low. Extremely low. Not zero, but low. One reason involves the kinds of stars capable of producing long-duration gamma-ray bursts. Many appear to require specific conditions, particular masses, particular rotational properties, particular environments. Not every giant star becomes a gamma-ray burst source. Most do not. Similarly, neutron star mergers capable of producing short-duration bursts are relatively rare. The galaxy is large. Suitable targets are limited. Fortunately for Earth, we do not currently know of any nearby objects likely to produce an imminent gamma-ray burst aimed directly at us. That's always a pleasant sentence to hear from astronomers. Sometimes the universe provides reassuring updates. There's another perspective worth considering. The same gamma-ray bursts that could potentially threaten a planet are also responsible for expanding scientific knowledge. The danger and the value arise from the same source. Without their immense brightness, we couldn't detect them across billions of light years. Without their immense brightness, they wouldn't illuminate the early universe. Without their immense brightness, they wouldn't help reveal ancient galaxies and distant cosmic history. The characteristic that makes them potentially hazardous nearby is the same characteristic that makes them scientifically invaluable far away. Nature often works that way. Powerful phenomena rarely fit neatly into categories of good or bad. They simply exist. Their effects depend on circumstances. A volcano can destroy a landscape. It can also create new land. Radiation can damage living tissue. It can also provide essential medical treatments. Gamma-ray bursts follow a similar pattern. From a safe distance, they become extraordinary scientific tools. Too close, and the story changes considerably. There's an even broader lesson hidden here. Planets are not guaranteed permanent stability. Earth feels solid and enduring because human lives are short. Civilizations measure time in centuries. Geology measures time in millions of years. Astronomy measures time in billions. Viewed across those immense spans, planetary environments experience many influences: asteroid impacts, supernovae, climate changes, stellar evolution, and possibly, on rare occasions, gamma-ray bursts. The universe is dynamic. Earth's history reflects that reality. Life has survived remarkable challenges over billions of years. Mass extinctions occurred. Recovery followed. New species emerged. Complex ecosystems developed. The story continues. Gamma-ray bursts may represent one possible chapter in that larger narrative. Whether they have significantly affected Earth in the past remains uncertain. Whether they will do so in the future remains equally uncertain. What we do know is that these events possess enough power to matter under the right circumstances. and that's a remarkable thing to consider. An explosion occurring thousands of light years away could potentially influence a planet orbiting an entirely different star. Not because of physical debris, not because of direct contact, simply because radiation carries energy across enormous distances. The universe is more interconnected than it sometimes appears. A dying star can affect regions far beyond its immediate surroundings. A neutron-star merger can influence environments it never physically touches. Energy travels, information travels, consequences travel. That's part of what makes astronomy so fascinating. The events we study rarely remain isolated. They become part of larger stories, larger systems, larger histories. Astronomers are generally careful people. They spend their careers measuring things, checking calculations, questioning assumptions, and trying very hard not to exaggerate. This is one reason scientific papers rarely contain phrases like "absolutely unbelievable" or "you will not believe what happened next." Researchers tend to prefer cautious language, careful language, sometimes almost painfully careful language. So when a group of astronomers begins referring to an event as the brightest of all time, it's worth paying attention. Because something truly unusual has happened. On October 9th, 2022, detectors aboard multiple spacecraft suddenly recorded an extraordinarily powerful burst of gamma radiation. At first, nobody knew exactly how exceptional the event would turn out to be. Gamma ray bursts are already famous for their intensity. Astronomers detect them regularly. Most become interesting scientific observations. Some become major discoveries. A very small number become historic. GRB 2210009A belonged firmly in that final category. Within minutes, scientists around the world realized they were witnessing something extraordinary. The burst was exceptionally bright. Not slightly brighter than average, not merely impressive, exceptionally bright. So bright, in fact, that some instruments struggle to observe it properly. When astronomers build detectors, they must account for expected ranges of intensity. If an event becomes too bright, instruments can become saturated. It's a bit like trying to photograph the sun with settings designed for a cloudy afternoon. The camera simply wasn't expecting that much light. Something similar happened with several gamma-ray instruments observing GRB 2210009A. The event pushed equipment toward limits researchers rarely encounter. That alone attracted attention. Then the numbers started arriving, and the numbers were astonishing. To understand why astronomers became so excited, we need to remember how gamma-ray bursts are usually observed. Most bursts occur at enormous distances, billions of light years away. By the time their radiation reaches Earth, much of the energy has spread across vast regions of space. Even though the original explosion may have been extraordinarily powerful, the arriving signal is usually manageable. GRB 2210009A was different. Part of the reason involved distance, or more specifically, relative lack of distance. Now, it's important to keep the scale in perspective. The burst was not nearby in any everyday sense. Nobody was looking out a window and seeing it happen. The event occurred approximately 2.4 billion light-years away. That is an enormous distance. Light spent roughly 2.4 billion years travelling before reaching Earth. The event itself happened long before multicellular life became common on our planet. Yet in astronomical terms, 2.4 billion light-years is relatively close for a gamma-ray burst. Many bursts originate much farther away. This matters enormously. Imagine two identical flashlights. One is located across a room, the other is located on a distant mountain. The closer flashlight appears brighter, not because it produces more energy, but because less distance separates it from the observer. The same principle applies throughout astronomy. Distance dramatically affects apparent brightness. GRB 2210009 A benefited from an unusually favourable combination. It was intrinsically powerful, and it was relatively nearby. Together, those factors produced one of the brightest signals ever detected. Researchers quickly began calling it the boat, the brightest of all time. The nickname spread rapidly through the astronomical community. Unlike many scientific nicknames, this one wasn't particularly subtle. It was direct, simple, and surprisingly accurate. As more observations arrived, the justification became increasingly clear. The burst wasn't merely brighter than average. It wasn't merely one of the brightest. It appeared capable of outperforming almost every previously observed gamma-ray burst. The event was setting records. Naturally, astronomers wanted to know why. What made this burst so special? Had nature produced a uniquely powerful explosion? Was the viewing geometry unusually favourable? Had researchers simply gotten lucky? The answer appears to involve a combination of factors. The burst itself was extremely energetic. The jet orientation was favourable. The distance was advantageous. Several circumstances aligned simultaneously. The result was a cosmic event that stood out even among phenomena already famous for being extreme. One of the fascinating aspects of astronomy is that rare events often reveal new opportunities. Scientists spend years developing theories and instruments. Then a remarkable object appears and provides a chance to test everything. GRB 221009. A became exactly that kind of opportunity. Observatories around the world immediately focused attention on the burst. Space-based telescopes observed it. Ground-based telescopes observed it. Radio observatories joined the effort. Infrared instruments participated. X-ray facilities participated. For a time, much of the astronomical community concentrated on a single explosion occurring billions of light-years away. That's one of the privileges of studying the universe. The event may have happened long ago. The light arrives now. And when it does, researchers can mobilize an extraordinary network of scientific resources. The amount of data collected from GRB 221009A was immense. Scientists monitored the afterglow. They tracked how brightness changed over time. They analysed energy distributions. They examined interactions with surrounding material. The burst became one of the most thoroughly studied gamma-ray events in history. Every observation provided another clue. Every measurement helped refine understanding. Yet one feature remained especially remarkable. The burst wasn't merely bright in gamma rays. Its influence appeared across multiple wavelengths. The afterglow persisted. Researchers continued gathering information long after the initial flash had faded. This persistence proved invaluable. Remember how frustrating gamma-ray bursts were during the early decades of research. The flashes appeared suddenly, then disappeared. Astronomers struggled to collect enough information. Modern observatories operate very differently. When a major burst occurs, automated systems respond rapidly. Telescopes redirect themselves. Alerts spread globally. Data begins accumulating almost immediately. GRB 221009. A benefited from this modern infrastructure. Scientists were ready. The burst arrived. The instruments responded. And the resulting scientific harvest was extraordinary. Another reason the event attracted attention involved its rarity. Astronomers understand probabilities fairly well. They spend much of their time studying events that occur across immense populations and vast stretches of time. Gamma-ray bursts are already uncommon. A burst as bright as GRB 221009A is considerably rarer. Some researchers estimated that an event of comparable brightness might appear only once every several thousand years. Different studies produce slightly different numbers. The exact estimate remains uncertain. What isn't uncertain is that the event was unusual. Very unusual. The astronomical community understood this almost immediately. It's a bit like witnessing a solar eclipse. You know you're seeing something rare. You know future researchers will continue discussing it for years. Observations collected during the event may become important references for future work. GRB 221009A produced exactly that feeling. Astronomers recognized they were witnessing a benchmark event, one that future studies would frequently reference. Interestingly, the burst taught scientists something about dust as well. At first glance, dust may not sound particularly exciting compared with relativistic jets and cosmic explosions. Yet dust plays an important role throughout astronomy. Interstellar dust scatters light, absorbs radiation, shapes observations. GRB 221009A generated unusual rings visible in X-ray observations. These rings formed because radiation interacted with dust clouds located between the burst and Earth. The effect created beautiful structures. More importantly, it provided useful scientific information. Researchers could study the dust itself. The burst became both a target and a tool. That's one of the recurring themes of gamma-ray astronomy. The brightest explosions often illuminate much more than their own origins. They reveal details about everything lying between source and observer. Another fascinating aspect involved sheer scale. Astronomers often struggle to communicate the energy involved in gamma-ray bursts. The numbers become enormous very quickly. Yet GRB 221009A forced researchers to confront those scales directly. The event reminded everyone how extreme these explosions can be. Even after decades of study, even after thousands of observations, nature remained capable of producing something larger than expected. This happens surprisingly often in astronomy. Scientists identify a category of object. They develop theories, they gather observations, then the universe presents an extreme example. Something brighter, something larger, something faster. GRB 221009A became that kind of example. The burst pushed existing understanding toward its limits, not beyond those limits. But close enough to generate valuable questions. Could similar events be even brighter? How often do they occur? What conditions create them? How narrow was the jet? What role did orientation play? Researchers continue investigating those questions today. The story isn't finished. That's another important lesson. Scientific discoveries rarely conclude neatly. Observations generate answers. Answers generate new questions. The process continues. GRB 221009A solves certain mysteries while creating fresh avenues of investigation. Astronomers wouldn't want it any other way. A completely solved universe would be considerably less interesting. There was also something almost poetic about the timing. Not poetic in a mystical sense, simply remarkable. The explosion itself happened approximately 2.4 billion years ago. At that time, Earth looked completely different. Complex plants had not yet colonized land. Dinosaurs were unimaginably far in the future. Human beings were even farther away. The burst began its journey through space long before anything resembling civilization existed. For billions of years, the radiation traveled. Eventually, in October 2022, it arrived. Humanity happened to possess the necessary technology. Detectors were operating. Telescopes were available. Researchers were ready. A signal that began traveling before complex terrestrial ecosystems emerged finally reached a technological species capable of understanding it. That's a remarkable chain of events. Astronomy frequently produces moments like that. Moments where cosmic timescales and human curiosity briefly intersect. GRB 221009A provided one of the most dramatic examples in recent memory. Even now, scientists continue analyzing data collected from the event. Research papers continue appearing. Models continue improving. The burst remains a rich source of information. It will likely remain important for years to come. Future gamma-ray bursts will undoubtedly be discovered. Some may challenge its records. Nature has surprised astronomers before. It will almost certainly do so again. For now, however, GRB 221009A stands as one of the most extraordinary gamma-ray bursts ever observed, a cosmic explosion so bright that it earned a nickname almost immediately, a burst so powerful that instruments around Earth took notice, a signal that travelled for billions of years before announcing its arrival, and perhaps most importantly, a reminder that even after decades of studying gamma-ray bursts, the universe still retains the ability to astonish us. Of course, observing an event like the boat raises another interesting question. How exactly do astronomers detect these brief cosmic catastrophes in the first place? Long before astronomers can study a gamma-ray burst, they first have to catch one. That sounds simple. In reality, it is one of the most challenging tasks in modern astronomy. Imagine you're responsible for monitoring every lightning strike on Earth. Now imagine the lightning can appear anywhere at any moment. Some flashes last only fractions of a second. Many occur on the far side of the planet. You receive no advance warning, and after each flash, you must immediately determine where it happened, how powerful it was, what caused it, and whether other scientists should start observing the aftermath. Even that comparison falls short. Gamma-ray burst detection is considerably more difficult. The events occur across the entire sky. They can originate billions of light years away. Most last only seconds, some last less than a second. And because gamma rays cannot penetrate Earth's atmosphere efficiently, scientists can't simply place telescopes on mountaintops and wait. The atmosphere protects life on Earth from dangerous radiation. That protection comes with a trade-off. The very radiation astronomers want to observe never reaches most ground-based instruments. As a result, gamma-ray astronomy largely takes place in space. If you want to observe gamma-ray bursts properly, you need detectors above the atmosphere. That realization shaped the entire field. Modern gamma-ray burst research depends heavily upon spacecraft. Every major discovery, every major catalogue, every major breakthrough. All begin with instruments orbiting far above Earth's surface. The process starts with constant vigilance. Unlike traditional telescopes that point towards specific targets, many gamma-ray observatories spend their time watching enormous portions of the sky. They're essentially cosmic sentries, always alert, always monitoring, always waiting for the next burst. The reason is straightforward. Nobody knows exactly when the next gamma-ray burst will occur. A giant star doesn't send a warning message before collapsing. Neutron stars don't announce merger schedules. The universe operates according to its own timetable. Scientists therefore build systems capable of detecting surprises, and surprises arrive regularly. Some of the most important spacecraft in gamma-ray astronomy were designed specifically for this challenge. One of the most famous examples is NASA's Swift Observatory. Launched in 2004, Swift transformed the study of gamma-ray bursts. The name itself reveals the mission's philosophy: speed, rapid response, quick action. Swift was built to detect gamma-ray bursts and then immediately turn its instruments toward them. This may not sound revolutionary at first, yet it solved one of the greatest frustrations in gamma-ray astronomy. For decades, researchers struggled because bursts disappeared so quickly. The gamma rays would arrive, the burst would end, and by the time telescopes began observing, valuable information had already vanished. Swift changed that. The spacecraft continuously monitors large regions of the sky using a specialized gamma-ray detector. When a burst appears, the spacecraft automatically calculates its position. Then something remarkable happens. Swift physically reorients itself. The entire spacecraft turns. Additional telescopes on board immediately begin observing the source: X-ray telescopes, ultraviolet instruments, optical instruments. Within minutes, scientists can begin studying the afterglow, sometimes even faster. What once required hours now happens almost instantly. This dramatically increased the amount of information researchers could collect. Another important observatory is the Fermi Gamma Ray Space Telescope. Fermi studies some of the highest energy phenomena in the universe. Gamma-ray bursts are among its specialties. Unlike Swift, which emphasizes rapid follow-up observations, Fermi focuses heavily on measuring extremely energetic radiation. Together, these spacecraft complement each other beautifully. One identifies and tracks bursts, the other provides detailed information about high-energy emissions. Modern astronomy often works this way. No single instrument does everything. Instead, multiple observatories collaborate. Each contributes different pieces of information. The combined result becomes far more powerful than any individual system. What's particularly impressive is the speed involved. A gamma-ray burst appears, spacecraft detect it, computers calculate coordinates, alerts are transmitted around the world. Ground-based observatories receive notifications, telescopes begin moving, researchers start collecting data. All of this can happen in minutes, sometimes even seconds. The response network resembles an emergency communication system, except the emergency is occurring billions of light-years away. And instead of firefighters or rescue teams, astronomers rush to investigate. There is something wonderfully human about that. A distant star explodes. The light travels for billions of years. Then it arrives. And within moments, observatories across Earth are paying attention. Astronomy has become a global enterprise. The response to gamma-ray bursts demonstrates that beautifully. When a particularly important burst appears, scientists from numerous countries begin working simultaneously. Spacecraft contribute observations, ground observatories contribute observations, radio telescopes join the effort, infrared observatories participate. The entire astronomical community effectively mobilizes. This coordinated approach is essential because gamma-ray bursts evolve rapidly. The initial gamma rays may disappear almost immediately. The afterglow changes with time, brightness decreases. Different wavelengths become important at different stages. Missing the early observations can mean losing valuable information forever. Imagine arriving at the scene of a fireworks display several hours after it ended. You might still see smoke, you might find debris, but the most dramatic part is already gone. Gamma-ray bursts present a similar challenge. The earlier observations begin, the more information scientists can recover. This urgency explains why automation plays such a critical role. Human reaction times simply aren't fast enough. Suppose a gamma-ray burst appears while astronomers are asleep, or travelling, or conducting unrelated research. Waiting for human intervention could waste precious time. Modern systems therefore make many decisions automatically. Detectors identify bursts, software calculates positions, alerts are distributed immediately. Only afterward do scientists begin detailed analysis. Automation doesn't replace researchers, it gives them a head start. Another fascinating aspect involves localization. Detecting a burst is only the first step. Scientists must also determine where it came from. That turns out to be surprisingly difficult. Imagine hearing a sudden sound in a dark room. You know something happened. Determining the exact source requires additional information. Gamma-ray detectors face similar challenges. The burst arrives, the instruments record it, but identifying the precise location requires careful analysis. Early gamma-ray astronomy struggled enormously with this problem. Researchers could detect bursts. Pinpointing them accurately proved much harder. The situation improved dramatically as technology advanced. Modern observatories can often determine positions with impressive precision. That precision enables follow-up observations. Without accurate coordinates, telescopes wouldn't know where to look. Finding an afterglow would become far more difficult. The ability to localize bursts transformed the entire field. Suddenly, astronomers could identify host galaxies, measure distances, study environments, connect bursts with specific astrophysical events. The mystery began unraveling. Distance measurement represents another crucial step. Knowing where a burst appears on the sky isn't enough. Scientists also need to know how far away it is. This usually involves studying the afterglow. As we discussed earlier, distant objects exhibit redshift because the universe expands. The farther away the source, the greater the redshift tends to be. By measuring this effect, researchers estimate distance, and once distance becomes known, the true scale of the event emerges. This is often the moment when astronomers realize just how powerful a burst actually was. A bright burst nearby is interesting. A bright burst billions of light years away is extraordinary. Distance transforms interpretation. A great deal of gamma-ray burst science revolves around that principle. The same observation can imply very different physical realities depending on how far away the source turns out to be. Another important development in recent years involves multi-messenger astronomy. The name sounds complicated. The idea is surprisingly elegant. For most of astronomical history, scientists relied almost entirely on electromagnetic radiation. Visible light, radio waves, X-rays, gamma rays. Different forms of light carried information from distant objects. Multi-messenger astronomy expands that toolkit. Instead of relying solely on light, researchers now combine multiple forms of information. Gravitational waves, neutrinos, electromagnetic radiation. Each messenger provides unique insights. The most famous example involving gamma-ray bursts occurred in 2017. Two neutron stars merged. The event produced gravitational waves. Those waves reached Earth and were detected. Almost simultaneously, a short gamma-ray burst appeared. For the first time, scientists observed the same cosmic catastrophe through multiple channels. It was a historic achievement. Imagine trying to understand a concert by watching it through a window. You can see the musicians. Now imagine someone opens the window, suddenly you can hear the music as well. Your understanding improves dramatically. Multi-messenger astronomy works similarly. Each messenger reveals different aspects of the event. Together they provide a richer picture. The future of gamma-ray burst research will likely depend heavily on this approach. More gravitational wave detectors are coming online. Neutrino observatories continue improving. Gamma-ray instruments become increasingly sophisticated. The combination promises exciting discoveries. Researchers may eventually observe events that challenge existing theories. The universe has a habit of doing that. Every time scientists believe they understand a phenomenon completely, nature often provides a new surprise. Gamma-ray bursts have already demonstrated this repeatedly. There is also a practical challenge many people rarely consider: data volume. Modern observatories generate enormous amounts of information. Every burst produces measurements, spectra, timing information, brightness curves, images. Researchers must store, process, and analyze all of it. Astronomy increasingly depends on advanced computing. Without powerful computers, much of modern gamma-ray burst science would be impossible. Machine learning techniques are becoming more common as well. Algorithms help identify patterns. Software helps classify bursts. Automated systems assist with rapid decision-making. The tools continue evolving. Yet despite all this technology, there remains something fundamentally simple about the process. A detector waits. The universe provides a signal. Scientists try to understand it. That basic relationship hasn't changed. The instruments are more sophisticated. The mathematics is more advanced. The observatories are more powerful. Curiosity remains the same. Researchers still experience excitement when an unusual burst appears. They still wonder what caused it. They still ask questions, and they still chase answers. One of the most remarkable aspects of this entire enterprise is that the objects being studied no longer exist by the time we observe them. A giant star collapses. A neutron star merger occurs. The event ends. Billions of years later, the information arrives. Astronomers reconstruct the story from traces carried by light and other messengers. It's a bit like solving an ancient mystery using evidence preserved across cosmic time. The detective work never really ends. Every burst adds another clue. Every observation refines the picture. And every major discovery raises fresh questions. Even with all our modern technology, some mysteries remain stubbornly unsolved. Scientists understand much more about gamma-ray bursts than they did during the era of the Vela satellites. Yet important uncertainties persist. How exactly are the most powerful jets launched? Why do some bursts become dramatically brighter than others? Are there categories of gamma-ray burst we haven't discovered yet? Could entirely new mechanisms exist? The universe has not revealed all its secrets. What if humanity ever found itself close enough to witness one of these events directly? Not close enough to be endangered, just close enough to truly see it. What would observers experience? What would appear in the sky? And would the sight be beautiful, terrifying, or perhaps a combination of both? Suppose, for a moment, that astronomers receive extraordinary news, not alarming news, not the sort of announcement that sends people rushing toward bunkers or stockpiling canned food. Instead, imagine researchers discover that a gamma-ray burst is going to occur relatively nearby by cosmic standards, and the geometry is such that Earth will be able to observe the event safely. No danger, no catastrophic consequences, just an unprecedented opportunity to witness one of the universe's most powerful explosions from a much closer vantage point than usual. What would humanity actually see? The answer is more complicated than many people expect. Science fiction has conditioned us to imagine giant explosions dominating the sky, massive fireballs, expanding shock waves, brilliant cosmic flashes visible for weeks. Reality, as usual, prefers its own approach. The first thing to remember is that gamma rays are invisible. Human eyes cannot detect them. If a gamma-ray burst occurred somewhere in the galaxy and released its initial radiation toward Earth, nobody would suddenly look upward and see a giant beam crossing the heavens. The burst itself would initially be detected by instruments. Computers would notice, spacecraft would notice, astronomers would notice. The average person standing outside might see absolutely nothing at first. That fact surprises many people. After spending hours discussing the most powerful explosions in existence, it feels strange to learn that they can arrive invisibly, yet that's often how astronomy works. The universe is full of phenomena occurring beyond direct human perception. Radio waves, infrared radiation, ultraviolet light, X-rays, gamma rays. Our eyes evolved to detect only a narrow slice of reality. Technology extends that range. Without it, much of the cosmos would remain hidden. Still, while the initial gamma rays are invisible, the aftermath could become spectacular. Suppose the burst originated from a collapsing giant star. The resulting supernova might eventually become visible. Depending on distance, the star could appear extraordinarily bright. Perhaps bright enough to rival planets. Perhaps bright enough to cast shadows at night. Possibly even visible during daylight under exceptional circumstances. Human history contains records of supernovae bright enough to attract widespread attention. Ancient observers documented several such events. A nearby gamma-ray burst progenitor could produce something similarly dramatic. Imagine walking outside after sunset. The familiar stars appear overhead. Then you notice an additional point of light. Brighter than Venus, brighter than Jupiter, possibly brighter than every star in the sky. A new object has appeared. Night after night it remains visible. For weeks or months, it dominates astronomical conversation around the world. People take photographs, scientists gather data, news organizations discuss the event endlessly. Entire generations remember exactly where they were when the new star appeared. That scenario is entirely plausible for a sufficiently nearby supernova associated with a gamma-ray burst. Of course, the burst itself remains the main attraction scientifically. Astronomers would respond immediately. Every available instrument would become involved. Space observatories, ground observatories, radio telescopes, infrared facilities. Everything capable of observing the event would likely participate. The amount of data collected would be unprecedented. Researchers already become excited when a gamma-ray burst occurs billions of light-years away. A nearby event would generate enormous interest. It would probably become one of the most studied astronomical phenomena in history. The scientific value would be extraordinary. Scientists could observe details normally hidden by distance: jet formation, afterglow evolution, interactions with surrounding material. Every stage of the process would become clearer. Questions that have remained unresolved for decades might finally receive answers. It's difficult to overstate how valuable such an event would be. Astronomers spend entire careers hoping for opportunities like that. Fortunately, opportunities and dangers are not always the same thing. A burst can be close enough for excellent observations while remaining far enough away to avoid serious consequences. Space is large, very large. Those distinctions matter. Now let's consider another possibility. Instead of a collapsing giant star, suppose the nearby event involves neutron stars. What might observers experience then? Again, the initial gamma rays would remain invisible. The merger itself would not resemble a giant explosion in the sky. Yet follow-up observations could reveal something remarkable. The resulting kilonova might become visible. For a brief period, the event could shine with impressive brightness. Astronomers would track changes in color, brightness, spectral properties. The entire process would provide an extraordinary opportunity to study the creation of heavy elements. Remember what neutron star mergers produce: gold, platinum, various other heavy elements. A nearby merger would allow scientists to investigate those processes in unprecedented detail. Researchers often describe astronomy as a kind of natural laboratory. The universe performs experiments we could never conduct ourselves. Gamma-ray bursts represent some of the most extreme experiments available. A nearby example would essentially provide front-row seats, at a safe distance, of course, a very safe distance. There is another interesting question hidden inside this discussion. How close has Earth ever been to a gamma-ray burst source? The answer remains uncertain. Astronomers can identify remnants of ancient supernovae. They can study nearby neutron stars. They can reconstruct portions of stellar history. Yet tracing every past gamma-ray burst is much more difficult. The evidence often disappears. The bursts themselves are brief. The sources evolve. The galaxy changes. As a result, many ancient events leave only indirect clues. It's entirely possible that gamma-ray bursts have occurred relatively near Earth during the planet's history. Whether any significantly influenced life remains an open question. Researchers continue investigating. The story is not fully written yet. One of the fascinating things about astronomy is how often uncertainty remains. People sometimes imagine science as a collection of completed answers. In reality, science is full of ongoing investigations. Gamma-ray bursts provide an excellent example. Scientists understand vastly more than they did 50 years ago, yet important mysteries remain. Could something even more powerful exist? At first glance, the question sounds almost unfair. Gamma-ray bursts already sit near the top of the cosmic power rankings. They outshine galaxies. They release extraordinary amounts of energy. They can remain visible across billions of light-years. Surely there must be a limit, and indeed, there are limits. Physics imposes constraints. The universe cannot produce infinite energy. Matter is finite. Processes operate according to physical laws. Nevertheless, the universe has a long history of surprising astronomers whenever they become too confident about maximum values. For much of human history, stars seemed impressive enough. Then supernovae entered the picture. Supernovae seemed extraordinarily powerful. Then gamma-ray bursts appeared. Each generation discovers something more extreme. It's therefore reasonable to ask whether gamma-ray bursts represent the final answer, or merely the current answer. One candidate often enters these discussions: supermassive black holes. Specifically, the events that occur when stars wander too close. A star approaching a supermassive black hole can experience what astronomers call a tidal disruption event. The black hole's gravity becomes stronger on one side of the star than the other. The difference stretches the star, pulls it apart, and ultimately destroys it. The resulting energy release can be enormous. Some tidal disruption events produce powerful jets and extraordinary luminosities. They differ from gamma-ray bursts, yet they demonstrate that nature still possesses multiple pathways toward extreme energy production. Another contender involves quasars. Quasars are powered by supermassive black holes actively consuming matter. When large amounts of material spiral inward, tremendous energy emerges. Some quasars become visible across enormous fractions of the observable universe. In terms of total energy output sustained over long periods, quasars can rival entire galaxies. They're not explosions, they're engines. Yet they remind us that cosmic power comes in many forms. Then there are speculative possibilities. Astronomers occasionally encounter observations that resist easy classification. Unusual transients, mysterious bursts, unexpected signals. Most eventually receive explanations. A few remain puzzling. The universe has not promised that gamma-ray bursts represent the ultimate expression of astrophysical violence. Future discoveries may reveal entirely new categories of phenomena. History suggests caution before declaring any ranking permanent. That said, gamma-ray bursts remain extraordinary. Even if something more powerful exists, it would have difficult competition. The bursts occupy rare territory. The combination of energy release, luminosity, speed, and visibility places them among the most extreme events known. Finding something dramatically more impressive would not be easy. Researchers occasionally discuss theoretical objects capable of producing even greater energies. Some involve exotic conditions in the early universe, others rely on speculative physics. Cosmic strings occasionally appear in these conversations. Certain hypothetical black hole processes appear as well. At present, however, evidence for such phenomena remains limited or uncertain. Gamma-ray bursts possess a major advantage. They are unquestionably real. We've observed them, measured them, studied them extensively. They're not merely theoretical possibilities, they're active participants in the modern universe. Perhaps that's what makes them so fascinating, not simply their power, not simply their brightness, but their reality. Somewhere in the observable universe, giant stars continue dying. Neutron stars continue merging. Jets continue racing outward at nearly the speed of light. Gamma-ray bursts continue crossing billions of light years. The events aren't historical curiosities, they're ongoing features of cosmic life. And occasionally, one of those bursts becomes so bright that astronomers around the world stop what they're doing and pay attention. Yet despite everything we've learned, important mysteries remain. Scientists understand how many gamma-ray bursts form. They understand much of the underlying physics. They understand why the bursts become visible across such extraordinary distances. Still, several fundamental questions refuse to disappear. Questions about the earliest stars. Questions about the most extreme environments. Questions about whether entirely unknown varieties of burst may still await discovery. In other words, the story isn't finished. Not even close. Throughout our exploration of gamma-ray bursts, we've spent a great deal of time looking backward. Backward to the Cold War and the Vela satellites. Backward to ancient stars reaching the ends of their lives. Backward to neutron stars spiraling together over billions of years. Backward to explosions whose light began travelling toward Earth long before human beings existed. That approach is natural, because astronomy often functions as a study of history. The farther we look into space, the farther we look into the past. Gamma-ray bursts are among the best examples of this principle. Many of the bursts detected today occurred billions of years ago. The explosions are over, the stars are gone, the galaxies have continued evolving, only the light remains in transit. Yet once scientists began understanding these extraordinary events, another question gradually emerged. Could gamma-ray bursts tell us something about the future as well? Not the future in a fortune-telling sense. Astronomy doesn't work that way. Nobody is using gamma-ray bursts to predict lottery numbers or forecast next week's weather. Instead, researchers wonder whether these explosions might reveal clues about how stars, galaxies, and even the universe itself will continue evolving over enormous spans of time. The answer turns out to be surprisingly interesting. Let's begin with a simple observation. Gamma-ray bursts do not occur randomly. Every burst requires specific conditions. Massive stars must form. Neutron stars must exist. Binary systems must survive long enough to merge. Certain physical environments must develop. The bursts therefore reflect the broader history of cosmic evolution. If we understand how gamma-ray bursts change over time, we may learn something about how the universe itself changes over time. Imagine walking into a forest. You notice young trees, old trees, fallen trees, new saplings emerging from the ground. By studying the population, you can learn something about the forest's past and future. The same logic applies on cosmic scales. Gamma-ray bursts form part of a much larger ecosystem. They reveal information about stellar populations, galaxy evolution, and the long-term behavior of matter throughout the cosmos. One of the most intriguing discoveries involves the early universe. Astronomers have found evidence suggesting that gamma-ray bursts may have been more common during certain periods of cosmic history. This isn't entirely surprising. The early universe differed substantially from the one we inhabit today. Galaxies were younger. Star formation rates were often higher. Massive stars may have been more abundant in some environments. If giant stars serve as the progenitors of many gamma-ray bursts, then changes in stellar populations naturally influence burst frequency. In other words, gamma-ray bursts can act as indicators of how actively the universe was producing massive stars. The bursts become historical markers. By studying them, researchers reconstruct ancient periods of cosmic activity. And if we understand how those periods evolved into the present day, we gain insight into where things may be heading next. Another fascinating connection involves stellar chemistry. When the universe first formed, it contained mostly hydrogen and helium. Heavy elements were rare. In fact, many of the elements we encounter daily did not exist at all. There was no iron, no gold, no oxygen, no carbon. Those elements had to be manufactured later by stars. Generation after generation of stellar evolution gradually enriched the cosmos. Massive stars played a crucial role. Supernovae played a crucial role. Neutron star mergers played a crucial role. Gamma-ray bursts frequently accompany some of these processes. As a result, they provide indirect clues about how the universe became chemically complex. That complexity matters enormously. Planets require heavy elements. Life requires heavy elements. Technology requires heavy elements. The entire chain leading from the Big Bang to human civilization depends upon cosmic enrichment. Gamma-ray bursts are woven into that story. When astronomers observe a distant burst, they're often observing part of the process that transformed a simple universe into a complex one. In a sense, the future of the cosmos depends on events like these. Not because gamma-ray bursts directly shape destiny, but because they participate in the ongoing cycle of creation and destruction that drives cosmic evolution. A giant star dies, heavy elements spread into space, future stars form, future planets emerge, the cycle repeats, the universe builds complexity through repetition. Gamma-ray bursts help mark some of the most dramatic moments in that process. Neutron star mergers tell a similar story. We've already discussed their role in creating heavy elements such as gold and platinum. That role extends far beyond individual explosions. Every neutron star merger contributes material to the larger galactic environment. Over billions of years, countless mergers enrich galaxies with heavy elements. Future generations of stars inherit that material. Future planetary systems inherit it. Future civilizations, if they exist, inherit it as well. Viewed from this perspective, gamma-ray bursts become part of a very long chain of cosmic cause and effect. The burst itself may last only seconds. Its consequences can persist for billions of years. That's one of the recurring themes in astronomy. Brief events often produce long-lasting outcomes. A stellar collapse may occur in moments. The resulting elements may remain part of the universe indefinitely. Researchers also study gamma-ray bursts because they may reveal information about the first generations of stars. This remains one of the great frontiers of modern astrophysics. The earliest stars formed in a universe very different from today's. Astronomers call these hypothetical first stars population 3 stars. They remain elusive. No confirmed example has ever been observed directly. Yet many scientists believe they existed, and not just existed. They may have been enormous, far larger than many stars common today. If such stars really formed, their deaths could have produced extraordinary phenomena, possibly including unusual gamma-ray bursts. This idea excites researchers because observing one of these ancient signatures would provide a glimpse into a period of history otherwise difficult to investigate. Imagine finding a photograph from humanity's earliest days. The image would be priceless. Ancient gamma-ray bursts may provide something similar for astronomy. They could preserve information from the universe's formative years, and if scientists learn how those earlier stars lived and died, they will better understand the path that eventually produced galaxies, planets, and life. The connection between gamma-ray bursts and the future becomes even more interesting when we consider timescales extending trillions of years forward. Human beings naturally think in decades. Civilizations think in centuries. Astronomy often thinks in billions of years. The universe itself may continue existing for incomprehensibly longer periods. Eventually, star formation will decline. Gas supplies will become depleted. Galaxies will age. The cosmos will look very different from the one we see today. What happens to gamma-ray bursts under those conditions? The answer appears straightforward. They become increasingly rare. Long-duration bursts depend on massive stars. Massive stars require active star formation. As star formation slows, fewer suitable progenitors exist. The universe gradually produces fewer opportunities for those explosions. Short-duration bursts tell a slightly different story. Neutron star mergers can occur billions of years after the original stars formed. Consequently, such bursts may continue appearing long after active star formation decreases. The universe possesses a kind of delayed reaction. Stars form. They die. Neutron stars remain. Eventually mergers occur. The bursts can continue long after the original stellar generation disappears. Even so, over sufficiently long periods, those sources also become scarce. The future universe may be quieter, less dramatic, less energetic. Gamma-ray bursts help illustrate that transition. They are tied to epochs when stars still actively shape cosmic evolution. Eventually, those epochs will pass. Another possibility occasionally discussed by astronomers involves entirely unknown classes of gamma-ray bursts. This may sound surprising given everything we've already learned. Yet history encourages humility. When the Vela satellites first detected mysterious flashes, nobody knew what they were. Decades later, scientists identified multiple categories: long bursts, short bursts, different progenitors, different physical mechanisms. The lesson is clear. Nature sometimes hides complexity beneath apparently simple observations. Could additional categories exist? Possibly. Researchers remain open to the idea. The universe is large enough to support surprises. Some bursts already resist easy classification. A few display unusual durations. Others exhibit unexpected energies. Most eventually receive explanations. Not all do. Every unresolved observation becomes an opportunity. Perhaps future instruments will reveal entirely new populations of events. Perhaps hidden varieties of gamma-ray bursts await discovery. Astronomy rarely rewards overconfidence. One reason researchers continue paying close attention is that gamma-ray bursts push physics toward its limits. Extreme gravity, extreme magnetism, extreme energy. These conditions provide opportunities to test theories under circumstances impossible to reproduce on Earth. Future observations may reveal subtle effects not yet detected. New physics is not guaranteed, but scientists remain interested. Whenever nature provides access to extreme environments, researchers pay attention. The most interesting discoveries often emerge at the boundaries of existing knowledge. There is also a broader philosophical dimension to all this. Not philosophy in an abstract sense, something simpler. Gamma-ray bursts remind us that the universe remains active. Stars are still forming, stars are still dying, galaxies are still evolving. The cosmos is not a static place. It never was. Sometimes astronomy can make distant objects feel frozen. A galaxy appears as a beautiful image. A nebula appears as a colourful cloud. A star appears as a steady point of light. Gamma-ray bursts reveal the dynamic reality hidden beneath those appearances. The universe changes continuously, sometimes quietly, sometimes violently. The bursts represent some of the most dramatic examples, and because they remain observable across billions of light years, they allow us to witness those changes across enormous stretches of time. In that sense, they connect past, present, and future simultaneously. A burst begins in the past. We observe it in the present. The information helps us understand the future evolution of stars and galaxies. Few astronomical phenomena span so many scales at once. Perhaps the most important lesson is that gamma-ray bursts are not isolated curiosities. They are part of larger cosmic processes: the birth of stars, the death of stars, the creation of heavy elements, the evolution of galaxies, the changing structure of the universe. Every burst belongs to a larger story, and that larger story is still unfolding. Astronomers continue building better instruments, more sensitive detectors, more powerful telescopes, more advanced gravitational wave observatories. The next generation of discoveries may answer questions that seem impossible today, or they may reveal entirely new mysteries. History suggests the second option is likely. The universe has repeatedly demonstrated a talent for exceeding expectations. Gamma-ray bursts once seemed impossible, then they seemed mysterious, then they seemed partially understood. Today they remain both understood and mysterious at the same time. Researchers know a great deal about them. Researchers still have much to learn, and perhaps that balance is exactly what makes them so compelling. The brightest explosions in the cosmos have illuminated more than distant galaxies. They have illuminated our own understanding. They've revealed how stars die, how matter transforms, how the universe evolves. Yet what do these brief flashes ultimately tell us about our place in a universe capable of producing such extraordinary events? Across this journey, we've spent time discussing some of the most powerful explosions ever discovered. We've followed mysterious signals from Cold War satellites. We've watched giant stars collapse into black holes. We've observed neutron stars spiraling together after billions of years of orbital decay. We've traced beams of gamma radiation across enormous stretches of space and time. We've examined events capable of briefly outshining entire galaxies. And yet, after all the numbers, all the physics, all the astonishing scales involved, there is a simple question waiting at the end of the road. What are we supposed to make of all this? Not as astronomers, not as physicists, simply as human beings. Because gamma-ray bursts occupy a peculiar place in our understanding of the universe. They are among the most violent phenomena known. Yet most people will never see one. They occur across distances so vast that they seem disconnected from everyday life. They unfold in environments so extreme that ordinary intuition struggles to follow. At first glance, they appear completely unrelated to the human experience. But astronomy has a habit of surprising us that way. Again and again, researchers investigate something distant, something ancient, something apparently irrelevant to daily existence, and eventually discover connections that weren't obvious at the beginning. Gamma-ray bursts are no exception. Let's start with something simple. Every atom in your body has a history. The oxygen you breathe, the calcium in your bones, the iron in your blood, the carbon that forms much of your physical structure. None of those elements existed immediately after the Big Bang. The early universe was remarkably simple. Hydrogen dominated, helium was common, heavier elements barely existed. The cosmos had not yet learned complexity. That would come later. Stars changed everything. Over billions of years, stellar furnaces manufactured heavier elements. Explosions distributed them. New stars formed. New planets emerged. Eventually life appeared. You are part of that chain. So am I. Every living thing on Earth is. When a giant star dies and produces a gamma ray burst, we tend to focus on the explosion, the brightness, the violence, the energy. Yet another story unfolds simultaneously. Elements are being redistributed. Matter is being recycled. The raw ingredients of future worlds are being scattered into space. Some distant planet orbiting a star that has not yet formed may eventually contain material launched outward during one of these explosions. The burst lasts seconds. Its consequences may last billions of years. That's a recurring theme in the universe. Short events often create long legacies. Human history provides familiar examples. A single decision can alter generations. A brief conversation can change a life. A momentary discovery can transform civilization. Cosmic history operates similarly. A collapsing star releases an extraordinary amount of energy. The event itself ends quickly. The aftermath continues almost indefinitely. There is something worth noticing here. The universe does not separate creation and destruction as neatly as humans sometimes do. We often think in categories: building versus breaking, beginning versus ending, life versus death. Nature is rarely that simple. The death of a massive star creates conditions for future stars. The destruction of one object becomes part of the construction of another. The collision of neutron stars generates heavy elements that may later become components of planets. The processes appear violent, yet they also contribute to creation. The same event can be both an ending and a beginning depending on where you stand. Astronomy teaches this lesson repeatedly. A supernova destroys a star. A supernova enriches a galaxy. A black hole forms. Future generations of stars inherit the consequences. Nothing exists entirely in isolation. Everything becomes part of larger cycles. Gamma ray bursts simply reveal those cycles in particularly dramatic ways. Another interesting aspect involves scale. Throughout this series, we've encountered numbers so large they almost lose meaning. Billions of years, billions of light years, hundreds of billions of stars, galaxies containing unimaginable quantities of matter. The scales involved can feel overwhelming. Sometimes people encounter astronomy and experience a strange reaction. They begin feeling small, insignificant, lost within a vast universe. It's understandable. The cosmos is enormous. There is no denying that. Yet astronomy can produce another reaction as well, one that receives less attention: wonder. Not because humanity is large, not because humanity dominates the universe, quite the opposite. The remarkable thing is that a species living on a small planet orbiting an ordinary star has learned to understand events occurring billions of light years away. Think about that for a moment. Gamma ray bursts happen in distant galaxies. The explosions are unimaginably remote. The stars responsible often died before Earth developed complex life. Yet somehow, a civilization emerged here. That civilization invented mathematics, built detectors, launched spacecraft, developed theories, and eventually learned how to reconstruct the stories of stars that vanished billions of years ago. That achievement is extraordinary, not because it makes us powerful, because it makes us curious. Curiosity may be one of the most remarkable characteristics life has ever produced. The universe creates stars. Stars create elements. Elements create planets. Planets create environments. And eventually, on at least one world, matter begins asking questions about itself. Gamma-ray bursts are part of that story. Not directly, not intentionally, yet they contribute to the larger chain of events, the atoms involved, the energy involved, the cosmic history involved. Everything connects. In some way, every scientific observation represents the universe examining itself. A burst occurs, the light travels, a detector receives the signal, a scientist interprets the data, the information becomes understanding. The process sounds simple, it's actually extraordinary. The universe is vast enough to produce gamma-ray bursts and subtle enough to produce minds capable of studying them. Those two facts coexist. Neither diminishes the other. Sometimes people ask what practical purpose astronomy serves. It's a fair question. After all, gamma-ray bursts are not solving traffic problems. They are not preparing dinner. They are not fixing household appliances. In the narrowest sense, many astronomical discoveries have little immediate impact on everyday routines. Yet human beings have always looked beyond immediate needs. Our ancestors crossed oceans, mapped continents, explored mountains, not because survival demanded every journey, but because curiosity demanded answers. Astronomy continues that tradition. Gamma-ray bursts remind us that exploration isn't limited to geography. There are still frontiers. They're simply farther away than previous generations imagined. The first humans explored valleys and rivers. Modern scientists explore neutron star mergers and relativistic jets. The motivation is surprisingly similar. We want to know what's out there. We want to understand how things work. We want to place ourselves within a larger context. Gamma-ray bursts help provide that context. They reveal a universe that is active rather than static, dynamic rather than frozen. Stars are not eternal. Galaxies evolve. Matter changes form. Energy moves from one place to another. The cosmos remains busy, even when it appears calm. That's worth remembering. The night sky often looks peaceful. Stars shine steadily. Constellations seem permanent. Everything appears quiet. Behind that appearance, however, the universe is constantly changing. Stars are forming. Stars are dying. Black holes are feeding. Neutron stars are colliding. Gamma-ray bursts are crossing intergalactic space. The apparent stillness is an illusion created by distance and timescale. Astronomy teaches patience. Events that seem motionless from a human perspective become dynamic when viewed across millions or billions of years. In a way, gamma-ray bursts represent concentrated reminders of that reality. They are moments when cosmic change becomes impossible to ignore. For a few seconds, an event releases enough energy to outshine galaxies. Then the burst fades. The universe continues. Another interesting lesson emerges from their rarity. Most stars do not produce gamma-ray bursts. Most stellar deaths are less dramatic. The conditions required are unusual. Specific masses, specific environments, specific physical circumstances. The rarity makes the events valuable scientifically, yet it also highlights something broader. The universe contains both ordinary processes and extraordinary processes. Most stars live relatively predictable lives. A few become legendary. Human experience isn't entirely different. Most days are routine. Occasionally something remarkable happens. The routine matters. The remarkable moments matter too. Gamma-ray bursts remind us that extremes exist, not because extremes are common, but because the universe occasionally pushes itself toward its limits, and when it does, the results can be astonishing. As our journey approaches its conclusion, it's worth returning to the beginning. Back to that simple question. What exactly is a gamma-ray burst? On one level, the answer is straightforward. A gamma-ray burst is a brief flash of extraordinarily energetic radiation, produced by some of the most extreme events in the universe. A giant star collapses. A neutron star merger occurs. relativistic jets emerge, gamma rays race outward. Astronomers detect the signal. That explanation is scientifically accurate, yet after everything we've discussed, it feels incomplete somehow, because gamma-ray bursts are also records of cosmic history, tools for studying distant galaxies, evidence of stellar evolution, sources of heavy elements, laboratories for extreme physics, windows into the early universe. They are many things simultaneously. Perhaps that's why they continue fascinating researchers. Every time scientists believe they understand the phenomenon fully, another layer appears, another question emerges, another mystery survives. The universe remains generous with unanswered questions, fortunately. A completely solved cosmos might be less interesting. Curiosity thrives when mysteries remain, and gamma-ray bursts still provide plenty of mysteries. Future observatories will detect new bursts, future astronomers will analyze new data, future discoveries will refine existing theories. Some current ideas may prove incomplete, others may survive. The story will continue, it always does. Somewhere in the observable universe, while these words are being read, a massive star may be approaching collapse. 2 neutron stars may be spiraling toward merger. A relativistic jet may be forming. A gamma-ray burst may already be racing across billions of light years. The signal won't arrive tomorrow. It may not arrive for millions or billions of years. Yet, it is travelling nonetheless, crossing darkness, crossing time, carrying information from one era of cosmic history toward another. And perhaps that's an appropriate place to end this evening's journey. Not with certainty, not with final answers, but with appreciation. Appreciation for a universe capable of producing events so powerful that they briefly outshine galaxies. Appreciation for the scientific effort required to understand them. Appreciation for the curious minds that continue asking questions. And perhaps most of all, appreciation for the fact that on a small planet orbiting an ordinary star, life evolved far enough to notice. The gamma-ray bursts will continue. The stars will continue living and dying. The universe will continue changing. And somewhere, sooner or later, another brief flash will appear in the darkness, beginning a journey that may one day tell a future civilization another story about how extraordinary the cosmos can be.